So we can start. Good morning. We can start work of our morning section. It's a great pleasure to introduce first speaker, Sezen Seçmen. And Sezen will go through the ultimate LHC physics prospects at very high luminosities. We have 30 minutes. Please, you can start.
Thank you very much, Professor Aliyev, and thanks to the organizers for inviting me to speak here. Indeed, I will be talking about the physics prospects at very high luminosity LHC. So, of course, since this conference has people from all areas of physics, I wanted to start with reminding the standard model of particle physics, which summarizes all of our current knowledge about elementary particles and and their interactions. And this information has been collected in work that lasted for more than 50 years and included theory and experiment. So standard model is a quantum field theory, and it combines, as I said, all our knowledge about particles and interactions. And here you can see it summarized nicely and neatly in a table. So we have point-like fermions that constitute matter, leptons and quarks. And we have spin-1 vector bosons, which are the force carriers through whose interactions through whose exchange matter interacts. And finally, we have the last component, the scalar Higgs boson, which was discovered at the LHC. The standard model is correct. However, it is not complete. It is there are still many questions that the standard model cannot answer. And here I list some of the questions. For example, origin of the mass. Why do particles have mass, and why do different particles have different masses? So this question has been answered more or less by the discovery of the Higgs boson, and of course, well, before that, by the invention of the Higgs mechanism. So this is one check mark. But there are many others. For example, the problem of flavor. Why do we have 3 fermion families with similar properties but different masses? There's no fundamental answer. Then there is the hierarchy problem. Why is the scale of electroweak interactions 10 to the 24 times smaller than the grand unification scale, which unifies electroweak and strong interactions? So then the problem of unification. Standard model only explains electromagnetic weak and strong interactions, and the gravitational force is different and much weaker, and this is not explained by the standard model. Then we have matter-antimatter asymmetry. Standard model cannot explain the origin of this asymmetry and why matter dominates our universe. And last but not least, we have the dark questions. We have dark matter. We have some experimental evidence for dark matter and dark energy, and standard model can explain none of these, the origin of these things. So obviously, we need something that is more generic, a more fundamental theory. And for that, we of course have many candidate theories, but the answer will be given by experiment. So how do we go from the standard model to a more fundamental theory that is built on the standard model? So there are 2 approaches. One is the indirect approach. We build experiments and we measure the properties of the standard model. We make experimental observations, and we try to find an anomaly, a discrepancy, an inconsistency in the standard model predictions, and we try to build a theory from there. So this is one approach. And the second approach is the direct approach, where we postulate a candidate new theory, or more than one new candidate theories that address the standard model's deficiencies, and we directly try to search for evidence for these theories. But either way, we do this through experimentation, of course. Now, there are a lot of questions that we can look for and that we can answer at an experiment such as the Large Hadron Collider. And I tried to make a chart here, and everything is actually connected. Like in the middle, we have BSM, or beyond the standard model, theories or questions, and these are connected to various parts of the standard model that we know, like QCD and electroweak physics, top, Higgs, flavor questions, and finally we have dark matter. So all these things are connected to each other with different questions that would lead us to the beyond the standard model. Now, okay, enough of introduction. We could now go to the LHC and HLLHC and what we are trying to do currently to answer these questions. You can see here a plan of the LHC, a schedule of the LHC, and it shows the timeline, the different years here, and the different energies that the collider had, and the different luminosities, instantaneous and integrated luminosities. So right now we are at the shutdown period. We are done with runs 1 and 2 of LHC, and we are about to start the so-called run 3 of LHC in the beginning of next year, hopefully. And of course, we are working a lot to analyze the current data sets that we have, and we are doing a lot of physics studies on different areas. But at the same time, there is a huge dedicated effort to build the next generation LHC, which is called the high luminosity LHC, as you can see in the frame here. So the high luminosity LHC will have a center of mass of 14 TeV, which is the ultimate energy that is aimed for LHC for the time being. And the instantaneous luminosity will be 5 times more of what we have right now. And this machine intends to collect a total integrated luminosity of 3 to 4 inverse attobars, which is really a lot. And this will bring a pileup that is, let's say, unwanted interactions per each hard interaction, 140 to 200 of these pileup interactions. Okay, so this is the schedule, and this is the machine that we are aiming at eventually at the LHC. And this new machine, the high luminosity LHC, brings a lot of opportunities and challenges. So the opportunities is obviously we will have much more data at very high energy, and having a lot of data means low statistical uncertainties and low systematic uncertainties in the experiment. So this is very nice. And but of course, to accompany the machine, the detectors such as ATLAS and CMS and all others will also be upgraded, are being upgraded, and they are being improved actually. So we will have improved detector capabilities and new detector features. But this is all good, but we also have some challenges such as high pileup, as I was mentioning, high beam-induced backgrounds and high radiation. So this will need improved techniques in triggering object reconstruction and analysis techniques. So I was mentioning upgrades to the detectors. Here's an example from the ATLAS detector, which summarizes the upgrades. For example, in the muon detectors, we are aiming for an improved coverage, and there will be a completely new design of inner tracking detector. And there will be upgrades to the colorimeters and triggers, and there will be a new end-cap high granularity timing detector, which didn't exist in the older runs. And there will be upgrades to trigger and data acquisition. And similar things are expected for the CMS detector. Again, we will have improved coverage of in all detectors, so we will be able to detect particles in let's say an extended geometry, and there will be again a new timing detector and upgrades in all sorts of other sub-detectors of the CMS experiment, so I won't go into detail here. Now, there have been a lot of physics studies at ATLAS and CMS to see, to explore the full potential at the HLLAC and its upgraded detector. So what kind of physics can we expect at the high luminosity LHC with these improved amount of data and improved detector capabilities? So there was actually a dedicated one-year workshop in 2017-18, which was a collaboration of LAC experiments and the theorists. And this resulted in writing some CERN yellow reports on standard model Higgs and beyond the standard model. And there were several recent technical design reports written by ATLAS and CMS. And now currently there's a SNOMES 2021 effort ongoing, which brings a new plethora of studies. And the focus of these studies is to continue and improve the current searches to extend sensitivity and design new searches that exploit specifically the new features of the detectors, and to develop new analysis strategies that would give us that would help us access scenarios with lower cross sections, lower acceptance, and to open new search channels in new models or the existing models. Now, two technical details about these studies, because these will come up in the plots that I'm gonna start showing just now. There were two different methods that ATLAS and CMS use for establishing physics sensitivity. And in doing the analysis that give us the physics result. The first method is the projections from present analysis. So we have the already existing analysis that are done with run 1 or run 2 data. So what we do, we take these analyses, these distributions, and then we project them to HLLAC energy and luminosity by making simple calculations. So that is method 1. That's an easier method. And the second method is to design completely new analysis from scratch using events, collision events with phase 2 specific detector simulation. So both of these methods have been used. Now, the second thing is the treatment of experimental uncertainties. Uncertainties are, of course, extremely important when we do such studies because we are trying to establish the sensitivity of high luminosity LAC. So there were several scenarios that were used that you will see in the plots, like the run 2 systematic uncertainties, which use the systematics that we have now, and the yellow report 18, which is a set of reduced uncertainties anticipated for phase 2, the HLLAC, and finally, statistical only case where we don't even have any systematic uncertainties. Okay, now I will start showing some physics prospects, starting with Higgs. These are, just to remind you, these are only several examples, and there are a lot of other studies, and it's important, especially for the non-high energy physicists, not to try to understand all detail, but just to, try to see the concept. Now, Higgs is indeed very important, and it's very relevant at the at the LHC, all of LHC, and it was discovered at the LHC. And why was LHC a Higgs machine? It was able to produce Higgs in 4 different production channels that you can see in these Feynman diagrams here. So Higgs can be produced in via several processes, and what's more, Higgs can decay into many different final states. And in the mass of the Higgs boson that exists, which is 125 GeV, a lot of these decay channels are visible at the LHC, and they have been so far observed. So therefore, the mass of the Higgs boson puts Higgs searches in a very interesting place, because we have many different probes for measuring Higgs and handling it at the LHC. So again, a lot of studies were done at the LHC, And of course, they will continue at the HLLHC. So a brief history of the Higgs. So maybe I just brushed through this. Discovery was announced at July 2012. Then observations started coming up in the different channels like Higgs 2W as a decay channel, and then observation happened in 2013 at various production channels like gluon fusion, vector boson fusion, WHWZ production. Then some other observations happened in harder channels like Higgs to tau tau or Higgs to BB. Or Higgs to mu mu more recently. So as you can see, there were a lot of probes, and we have seen that the Higgs existed in all these production and decay channels. But one thing to note is, even though the Higgs is discovered, the uncertainty with which we measure all these Higgs in all these channels is not sufficiently small. So the smaller the uncertainty, the more information we will have about Higgs. So that's why HLLHC, the increased luminosity, is extremely important for Higgs physics. So what kind of measurements are we expecting to do? And what kind of improvements are we expecting? So the very first thing, the cross-section and branching ratio measurements at high luminosity LHC. So what was done by ATLAS and CMS was to project or extrapolate the run-2 Higgs measurements in various production and decay channels, and to estimate the uncertainty and the different contributions from different uncertainties in different production and decay channels, as you can see in the plots here. So in the HLLHC, we will be able to measure Higgs with about 5% accuracy, which is actually quite good, and we will bring it to the situation that the theory uncertainties will be dominant. So experiment will have achieved its goal. Now, another important thing about Higgs and about measuring it as precisely as possible is to see if the Higgs that we are observing is the one that is predicted by the standard model. So this we can see by parameterizing the deviations in so-called modifiers to fermion and boson couplings to Higgs. So this is done in the way as you can see on the right. So we divide the cross-section that's observed with the cross-section that is predicted by the standard model, or we do the same for branching ratios. So if the Higgs standard model, all these modifiers should equal to 1. But if it's different from standard model, if other processes are involved, then the modifiers should not be equal to 1. So therefore, it's quite important to measure these modifiers with very good accuracy and precision. And as you can see, again, HLLHC will give us very low uncertainties for measurement of a lot of these modifiers and even the ratios between these modifiers. Now coming to another very important thing for HLLHC, which is the di-Higgs production. So di-Higgs is a flagship measurement at the HLLHC, and you can see the Feynman diagram here. So it allows to measure the trilinear Higgs self-coupling, and it will help to constrain the Higgs potential shape and nature of electroweak symmetry breaking. And this is also very sensitive to beyond the standard model physics. So sensitivity to any di-Higgs channel requires HLLHC. It cannot be accessed by the LHC, by the current LHC. And what's more, it requires combining all decay channels of di-Higgs. So we need to measure di-Higgs production in all sorts of decay channels and combine. So, and what's even more, we cannot make a discovery using one experiment, only CMS or ATLAS. We also need to combine both experiments. So di-Higgs measurements really require the ultimate power of LHC. But in the end, if we do these measurements, we will be able to, if you collect all these data, we will be able to make these measurements and make a statement about di-Higgs in the end. Now coming to Higgs mass, width, and Higgs to invisible. For Higgs mass, we expect measurement with 10 to 20 MeV accuracy, which brings about 10 times improvement to the standard model, to the current run-to measurements, which is very good. And the Higgs width, again, so there's a intricate indirect measurement for Higgs width that was developed at RAM1 and 2. And these measurements will also increase the accuracy of the width. Now, another very important, relevant thing, especially for beyond the standard physics, is to measure the branching ratio of Higgs decaying to invisible particles. Normally, in standard model, Higgs doesn't decay to invisible particles. It has a very, very low branching ratio. So if we somehow manage to observe Higgs decaying to invisible particles, this means that there is definitely some new physics effect ongoing. And again, this measurement will be sensitive to this sort of measurements, especially at the high luminosity LHC. Now, one last thing about the Higgs is beyond the standard model Higgses. So many beyond the standard model Higgses are predicting, beyond the standard models are predicting that some extra Higgs bosons. So these Higgs bosons can be lighter than the regular 125 GeV Higgs that we know, or heavier. So again, there are a lot of sensitivity studies done at the high luminosity LHC, and the measurements, or let's say the searches, will improve sensitivity by a lot when we go to the high luminosity LHC. Now, a very brief note on standard model prospects. Two things. This is actually pretty technical, more for the experts. One very important, interesting thing is vector boson scattering, which would allow us to probe the electroweak symmetry breaking mechanism and is also sensitive to beyond the standard model physics. So very recently, there's a CMS study that projected the WZ electroweak scattering measurements in the leptonic decay modes. And here you can see the increase in, the expected significance versus luminosity, increase in luminosity for the cross section of vector boson production and for the different polarizations of this production. Now, another note about the standard model physics is rare measurement of rare processes. So this is again quite relevant. There are rare processes in the standard model which are highly sensitive to BSM physics. And the more luminosity we have, the more sensitivity we would have to such processes. So one such process is the four-top production. And we currently expect 10 to 30% uncertainty in the cross-section from HLLHC, and this could be improved. And another thing, again, from top physics is the associated production of top pairs with W's, Z's, and photons. So there were again studies which will measure these processes in a precise way and try to see if there are any deviations from the standard model. Now, finally, this brings me to prospects for beyond the standard model physics. So there are a lot of candidate theories for beyond the standard model physics that try to answer different questions that the standard model physics cannot answer. Of course, this is just a random chart that I found from the internet, and this is by no means complete, but it just shows that, you know, different theories have different strengths, and there are a lot of theories out there. Now, the very first easiest thing we do when we are looking for beyond the standard model physics is to search for so-called high mass resonances. And well, in many new physics models, massive particles are predicted, and these particles decay to detectable standard model particles. So one can put these particles together and reconstruct the resonance. And these resonances can be explored by searching for a bump in the invariant mass distribution of the decay products. So I give some examples from such searches that are done, especially for the high luminosity LHC. So one search on the upper right is resonant Higgs-Higgs to 4B production. So you can see in the colored field histograms the standard model backgrounds in the invariant mass distribution, and then the line histograms show how the resonances would look if in case they exist. Of course, this is all simulation. So we can try to see how sensitive our measurement can be and up to what mass of resonance we can actually probe. And here there are two other examples looking for Z primes and W primes in leptonic channels. So this plot, well, what the value that we should look is the intersection of the two lines in the histogram. So the HLLAC sensitivity for Z prime is, for example, 6 TeV, whereas the current run 2 limit is less than 4 TeV. So we are expecting a huge improvement that comes with the extra luminosity. Okay, another model which is very well motivated is supersymmetry. It's a symmetry between bosons and fermions, and for every known standard model particle, there's a super partner with a different spin. And SUSY is a broken symmetry, therefore SUSY particles are much heavier than standard model particles. Of course, SUSY has a lot of free parameters as a theory, could be 100, even more. Therefore, SUSY particles have free masses, and these masses can vary, and we could have different final states, different particle masses, different cross-sections, branching ratios, etc. Therefore, there are many final states involving different particles' kinematic properties to be explored, and there are a huge plethora of searches looking for SUSY. Now, I just show a few. So there are some searches looking for top quarks and gluinos, which are the super partners of top quarks and gluons that we know from the standard model. So these are just new searches for done by ATLAS and CMS. And the important thing, so what's shown in these plots is the exclusion that is done versus masses of the supersymmetry particles. So we can see that the HLLAC exclusion, which is shown for the ATLAS plot with a line, is really improving the current run 2 sensitivity, which is shown in with the purple filled graph, let's say, area. And the same goes for the CMS search. Right. Now, another very important thing that we will have access to at the HLLHC is the long-lived particles. So many new scenarios predict particles, long-lived particles that decay away from the interacting point of the detector. And this leads to several unique and challenging signatures, as is summarized in the figure here. So we have, for example, disappearing tracks where we have a track that disappears in the tracker, displaced digits, displaced vertices, displaced conversions and photons, displaced leptons, etc. So there are a lot of interesting signatures to look at, and HLLAC will be in the race. So, and this will help us do some complementary studies. For example, there's a case searching for the so-called Higgsinos that are predicted in SUSY. And Higgsinos are charginos and neutralinos, which have dominant Higgs component. And if we manage to see these Higgsinos, we will know that SUSY and naturalness is favored as a model. So this is a direct probe of naturalness in supersymmetry. And one signature of these Higgsinos, so we can see the Feynman diagram here. So this chargino here, which is denoted by chi1 plus minus, is a Higgsino, and it decays to a neutralino and a W, or could be also some other particle. The thing is that the mass between the chargino and the neutralino is very, very small. So this leaves us with a signature of missing energy plus some soft decay products. And there are two complementary ways to search for this. In the case where the mass difference is larger, we look for, the charginos are more prompt, and we look for low momentum leptons plus large missing ET signature. So the result of this can be shown by the blue area in this plot here. And the second case is the smaller delta M case, where we have long-lived chargino decays. And in this case, the chargino decays to very soft pions, and then the soft pion cannot be detected, and chargino looks like a disappearing track.
Suzanne, I am very sorry, the your time is over.
Yes, yes, I know. I'm finishing right now. Yes. So indeed, we can do complementary searches. So there are other searches, there are other long-lived searches that we can do, but I'm not going to go over them. So one last thing is we can also do dark matter searches at the high luminosity LHC, and we will also have really increased sensitivity to dark matter searches. And this brings me to the end of my talk. Indeed, there are a lot of searches at the high luminosity LHC. I've only managed to show a few, and all references are there if you are interested. I don't know, maybe we can post the slide somewhere, and interested people can take a look. Thank you.
Thank you very much for your very interesting and comprehensive talk. Maximum one question, please, if you want. Can no questions. So in this case, we can start. I am invited our second speaker, Professor Alfred.
Sorry, may I ask a question?
Okay, you can ask, please.
Okay, thanks a lot. How we can observe the high Higgs bosons decay to invisible particles? How is it possible?
Okay. Yeah. So we do this in an indirect way. Actually, I stopped sharing. Maybe I share quickly again. Okay. So I go back to that slide. Yeah. The way we do this, so the invisible Higgs bosons, they give a signature of missing energy, but the Higgs boson is produced in association with a visible particle, like a high PT jet, or some forward particles, or a Z boson, etc. So we are looking at these particles. So we are we are measuring the visible Z boson or visible jet in association with a lot of energy imbalance, that is a lot of missing energy. So from that measurement, we make an interpretation of the Higgs model predictions, and that's how we can actually get some sensitivity.
Thank you so much.
You're welcome.
Okay, so I invite our second speaker, Professor Alfred J. Weymouth. He will go through turning force microscope in its side and starting a simple chemical bond. Please, you have 30 minutes, and please we can start.
Super, thank you so much. I hope you can hear me clearly. Good, I'll just assume that's yes. So I'm here talking to you from Regensburg in Germany, where I work with Professor Giesebel, and we perform typically scanning tunneling microscopy and atomic force microscopy. And today what I'd like to do on this nice Saturday morning is to talk with you about a very ubiquitous phenomenon, that is friction, and how we're studying friction, or how we are now able to study friction at the smallest natural limit, so that is of a single atom. And we had a lot of fun with this work, and again, I'm really happy to be able to show you some of this. So I'm going to start. We've had a few days of excellent talks, really all around the spectrum of various different topics. So this slide might seem a little basic, but let's just start with something very, very familiar to everybody, and that's this concept of sliding friction, which is again this force, or this description of a large number of forces that opposes motion. Okay, so we have some kinetic motion, but as two objects slide against each other, the kinetic energy gets dissipated into various forms, and they can go into breaking of chemical bonds. Typically phonons are created, and there can even be photons created in the case of triboluminescence. One very important aspect of sliding friction is that it is a non-conservative force. So if we were to slide, for instance, your hands against each other, you slide forward and then backward, the total work done by friction is not zero, right? Friction always acts opposite to the direction of motion. And how do we even understand macroscopic friction? I mean, when my two hands are rubbing against each other, we don't believe that every atom of the surface of one hand touches every atom of the surface of the other hand. No, actually what we think happens is that the friction properties are determined by so-called asperities. And here I've tried to draw you a little zoom in of three asperities kind of sliding against the surface. And these asperities are kind of groups of about tens, hundreds of atoms or so. And they really determine the friction properties of these sliding surfaces. All right. So given that these asperities are so important, it might not be a surprise that one of the best techniques to study friction, or one very good technique to study friction, is the so-called friction force microscopy. This is a daughter technique of atomic force microscopy, in which there's just a sharp tip. We press it down against the surface, and then we rub it against the surface there. I mean, it's like the old record players would do, so to say. The lateral forces that act upon this cause a little twisting of the tip. And if you can measure the twisting and you know the torsional spring constant, then you have direct access to these lateral forces. And the advantage again of reducing the size of one of these sliding surfaces. So let's just consider again what's going on. We're going to have our little tip. We're going to slide it over the surface again. But now what the advantage is that we can possibly have at the apex of this tip a single asperity. Okay. And in friction force microscopy, then you can be sensitive to so-called atomic friction or atomic corrugation. This was first reported, as far as I know, in 1987, and the citation's on the slide. And the idea here is that you've got your atoms of your tip, they kind of lock against the atoms of the surface, and they kind of hop from position to position. So if we were to plot the lateral forces, the frictional forces as a function of distance, and we go in one direction, then we can actually see this atomic corrugation here, all right, where we're moving to the right, friction is kind of acting to the left, that's why it's acting in the negative direction here. If we were to go the opposite way, we would expect kind of an equal and opposite lateral force applied. And one thing I just want to remind you of again, although I know everybody is familiar with it, is that what we can do with these force distance curves is we can integrate them if we have, for example, a closed loop. And that gives us direct access to the energy that has been dissipated. And that's going to be an important concept a bit later in the talk. Now, I don't perform friction force microscopy. We do kind of a variation of this theme here, and we perform lateral force microscopy. So this is done with a much stiffer cantilever, both in the lateral direction and in the vertical direction, which allows us to really use a whole bunch of techniques that have been pioneered in the STM and non-contact AFM community to do so-called tip engineering. So what we can do is we can poke the surface, we can take a look at it, we can pick up various molecules, and we can really have control over the apex of the tip. So we know one of the sliding surfaces down to the atomic level. And if we use surface science techniques, then we can also prepare the other surface down to the atomic level. So what we can do is we can really have a perfectly atomically known two sliding surfaces, and we can have that one of the sliding surfaces terminate in a single atom. Now, there's two other important aspects of this technique. One is that we're going to oscillate the tip laterally. We're going to drive it to oscillate left and right, so in the direction that we care about when we're studying friction. This is different than normal AFM, where you would oscillate up and down. But we're going to oscillate, and we're going to oscillate so small that the amplitude of oscillation is much smaller than the distance between two neighboring atoms, so the core-core distance. So we're going to oscillate with amplitudes less than an angstrom. And the second thing we're going to do is we've got hardware that controls the amplitude of this oscillation. So we measure the amplitude of this oscillation, and when we come close to the surface, if we experience sliding friction, if the energy is being lost somehow, then the computer will increase the so-called drive signal, so the signal that's making this oscillate. And by measuring that drive signal, we have direct access to the energy that is lost when the tip interacts with the surface. Now, in this slide here, what you can see, I've drawn a little sketch. The gold balls are supposed to represent metal atoms, probably copper. And then you see a dark circle, which is representing carbon atoms, and a red circle that's representing oxygen atoms. So this is this CO molecule that would be sitting either on a metal surface or possibly at the apex of a tip. And the CO molecule has been very important in the non-contact AFM community. I just want to give a little explanation as to why. The first thing is it's rather easy to prepare. So with a very sharp tip, you can come down to a CO that's sitting on the surface, and it will jump up to the apex of the tip. And the second thing, as you can see in the bottom of this slide, is that it's really able to provide shocking spatial resolution. So we can now look into flat organic molecules and really see a picture that's very similar to the ball and stick model. Now, your eyes might be able to pick up that the data on the bottom right-hand side of this slide isn't exactly the same as this ball and stick model on the bottom left-hand side. The hexagons are kind of stretched in one direction, if you will. And we understand that by the CO itself acting like a torsional spring. That is to say, when forces are pushing laterally on it, then it kind of starts to bend a little to one side. And one of our first experiments that we did with lateral force microscopy, because this is really the ideal technique to look at systems where pushing from the side matters, is we took a look at just a CO on the surface with a CO at the apex of our tip. So on the left-hand side of the slide, what you're seeing is just an atomic model, just a sketch here, where at the bottom, the copper surface is represented. It's copper 111. There's a single CO molecule on it. And at the top, you see this little kind of triangle form that's representing the tip with a CO molecule on it as well. And on the right-hand side of this slide, what you're seeing is the LFM image taken from it. Now, we record the so-called frequency shift, so how the frequency changes when the tip interacts with the sample. And this gives us a measure of the conservative force interactions. You can see the scale bar here is in newtons per meter, in fact. If we integrate newtons per meter, we get direct access to the lateral forces. So we don't get direct access to our measurements, but we need to do an integration step in there as well to get them. And what we did was we collected data at various heights and various distances away from a single CO with a CO on the tip. And we converted this into lateral forces. And so what you can see here is a plot that shows these lateral forces as a function of both vertical and horizontal lateral distances. And when you're kind of further away, then the force is negative. That means it's pointing towards the center. All right. And then as you get close, this force kind of is pushing you a little bit away. And this reminds you of these very typical interatomic potentials like Lennard-Jones or Morse, in which we describe the interaction between two atoms as being attractive when they're far away from each other, mainly due to van der Waals interactions. And then as we enter closer, maybe a chemical bond forms, or maybe they just start to have some repulsion due to the Pauli excursion principle. Now, I highlighted a few points in black, and those are the zero crossings of the lateral forces. Now, when the lateral forces are zero, then of course our torsional spring doesn't bend because there's no net force acting upon it. And what's very interesting about these points is that they fall very nicely on a circle here. And this is what one would expect if we were describing, indeed, these standard empirical potentials like a Morse or a Leonard-Jones potential here. All right. Of course, the radius of the circle is the bond length as described by a Morse potential here. So what this means is that if we have really just two molecules that are acting like torsional springs, and we consider their interaction due to the apex atoms, so the two oxygen atoms, as a Morse potential, that's what I'm sketching out here on this slide. So you've got the energy of a torsional spring, which is a half k theta squared, right? The angle squared. And then you've got it on the surface as well. And then a Morse interaction. What you can do is you can very well describe the total energy of the system. And when we can do that, we can have a simulation and we can ask how well it reproduces our data. And this is what I'd like to show you now. So this is our data up here, our LFM image, again, similar to what I showed you a few slides back. And to the right-hand side, there's our model output. Okay. I took a line scan cut of the data. I just want to make a few points, but took a line scan cut and you can see the model and the data agree really very beautifully here. And so it's amazing that this Morse potential, this empirical potential that is only spherically symmetric, has such good agreement with our data, but it's also the case that our COs can be described very nicely as these torsional springs here. And part of this work was determining the torsional spring constant of a CO molecule at the AFM tip. All right, now that's very well and good, but I haven't gotten to what I've promised you yet, right? I promised you friction, I promised you energy dissipation, and so far, all we've seen are COs interacting with each other, and there's not so much dissipation here. So let's get to where I would like to go. And again, I just want to make the point that this work is really a product of like standing on the shoulders of giants, so to say. I mean, I'm taking this concept of using a lateral force microscope. So this is a photograph taken from an article almost 20 years ago now from Franz Giesebel and coworkers when he was back in Augsburg University, different university. And you can see this kind of sharp sword-like object pointing down. That's the tip of the LFM, and it's going to oscillate kind of left, right. It's going to be driven to oscillate laterally over the surface. So we take this concept, right? We have the idea of a tip that's engineered at the atomic scale. And this image comes from this famous publication here from Leo Gross and coworkers, where they looked at the inside structure of a molecule. All right. And we're also going to combine the idea of looking at friction where both sliding surfaces are understood at the atomic level. And I just give you one example here. This is from René Pollack and the group of Ernst Mayr in Basel. And here they used normal force microscopy, but they picked up a molecule so they knew exactly where all the atoms were. Okay. Of course, we're going to do this at a little smaller length scale with a single atom at the apex of our tip. So it might not surprise you to hear that we decided to start with a CO terminated tip, because this tip, of course, we have a lot of experience with, and it's been very well studied. And the system that we chose to look at is a small organic molecule called PTCDA. And I chose this because the interaction with the CO tip and PTCDA has also been very well studied from the non-contact AFM community. So we had a lot of good fundamentals. I write here that these measurements, but actually all of the measurements that I'm showing you today were performed in ultra-high vacuum. We've got a system that's very similar to what Johannes Barth was showing on, I think his talk was on Wednesday. We worked at 5.5 Kelvin, so we've got a liquid helium bath, and we're using this Q+ LFM sensor. And this is a really fun tool because it gives us access to, we can perform STM. At the same time, we can measure the frequency shift, so we can have access to these conservative forces, these Newton per meter. And this is what I've been teasing you from the start. We also get access to the energy dissipation. Okay. So without any further ado, let's take a look at this system. So I'm going to show you an island of PTCDA molecules on copper, taken with our CO terminated tip, and this is an STM image of this, all right? And your eye can kind of pick out, so we're taking this at constant height. Sometimes STM, the tip moves up and down. In this tip is just standing in a flat plane above the surface. Each of these kind of larger blobs that you can see is a single PTCDA molecule that's lying approximately flat on the surface, not 100% flat, but approximately flat. And maybe your eye can pick up some internal structure where you can even kind of see these the 6 carbons, the rings that kind of go on inside it. And this allows us to overlay, as I've done, this ball and stick picture of the molecule on it. Now, we collected simultaneously lateral force microscopy data, and that's what I would like to show you here. So the tip is oscillating in the X direction. It's oscillating laterally in the X direction. We're looking at the top down. Okay, we do have our bias voltage applied, but it's rather small. Our amplitude is only 30 picometers, so that you can look down at the bottom right-hand corner of this image. The scale bar is 1 nanometer, so the oscillation amplitude is really very small, right? And what your eye can pick up is this beautiful, crisp view of the internal structure of these molecules. Now, there's one other important point I'd like to make with this image, and that is that you can kind of see that the bonds that are about perpendicular to the direction of oscillation, those are the ones that show up darkest. So some bonds are about parallel to the direction of oscillation, and those we cannot see as well. So you can kind of see the ones that are aligned almost in the Y direction. All right, those are very, very strong. And in fact, that's why we chose to take a closer look at the molecule that's outlined in purple on the right-hand side. Okay. So we zoomed into this, and we went closer and closer and closer and closer. So here's a picture. Here's the LFM picture. And again, as I said before, these kind of chemical bonds that are perpendicular to the direction of oscillation, they show very strongly. The double-headed arrow is approximately the width. It's actually a little bigger, so the amplitude of oscillation is a little smaller than that double-headed arrow that's in the picture here. All right. This is the LFM image. And now what I would like to do is I'd like to show you the energy dissipation image. All right. And here's what we see, this beautifully crisp image where we have some areas of the molecule. This is taken simultaneously with the previous image. So this is really the internal core structure of this molecule. And your eyes can kind of see, especially in the center, this C6 ring very clearly. And we have, really signals that go very high outside of our noise floor. Okay. And now what we wanted to do was to try to really understand this signal here. And so again, what we did was we went back to all of the foundation that's been laid from the AFM community, and we thought about how we could model this into this tip sample interaction. And I have to say, we did something very straightforward. We determined the position of our metal tip. Our CO at the apex acts like a torsional spring. So when you laterally push on it, it deflects, okay? The atoms of the PTCDA molecule are allowed to interact with the apex oxygen. This is very similar to the work we did with CO-CO interaction via an empirical potential. But important here is that these surface atoms, in this case, were not allowed to relax, okay? And the CO was only allowed to relax either to the left or to the right. So let's take a look at a CO. I'm going to show you a little simulation of it oscillating left and right over a single chemical bond. So here we go. We see this yellow circle at the top that's symbolizing our copper atom, our apex metal atom, and then we've got the CO molecule here. It's kind of bent off to one side due to the Pauli repulsion. The gray circle at the bottom of this is to represent the the chemical bond here. And now let's see what happens just in one oscillation when the tip moves right and left. Okay, you can see this motion. The CO kind of bends and then snaps over. And it bends back as it returns and snaps over. This is not while we are scanning. The tip is effectively in one position, just going right and left many, many times. So we're collecting the data. Now, what we can do with this model is we can plot the lateral forces as a function of the lateral distance. And that's what you see on the right-hand side of the slide. And there's a position just over this chemical bond where we can see some hysteresis. So the lateral forces that act as you move from left to right are different from those coming back. And this is exactly this dissipative energy that we saw first in friction force microscopy, where we now have a closed loop and we can see some energy that is being lost here. If the CO is too far away from the bond, okay, then the lateral forces in one direction are equal and opposite to those in the other. We don't see any dissipation. We only see it when we have this hysteretic loop here. In other words, where we really get some CO snapping over a chemical bond. So with this model, we can really apply it now. We can move the tip anywhere, perform an oscillation and calculate the energy loss and compare it to our data. So that's what we did. In this simple model, we only even modeled 6 carbon atoms of the PTCDA molecule. We allowed the CO to relax in one direction, but we got great agreement. So B and D are the measured energy dissipation and frequency shift, and we calculated C and E, this with our model. Now, some of you see it, there's a tilt to the energy dissipation, and that's because one of the challenges of this work is really to align the tip so it oscillates laterally. It's a few degrees off, but we can incorporate that very easily in a model and still get some excellent agreement with the data. There's one last very interesting aspect of this that I need to share with you, because friction is so ubiquitous, we kind of think it would be very, very easy to measure the energy loss as we snap over. But in these measurements, what we see is that they are very sensitive to vertical distance. So I'm plotting here on the bottom, that's the vertical distance. That's how high we are above the surface. And on the y-axis is the dissipated energy. And we only get a strong signal that's outside of our noise in a range of 10 picometers. That's it. So the black dots in this are the data. The red dots are our model. And actually the blue curve is an exponential fit, just to show how steep this increases with respect to distance. So when we are trying to observe this energy dissipation, we really have to go down picometer by picometer, or we're going to miss it. All right. And it's amazing to think that we're really only having substantial dissipation in this very, very small Z window. It's totally unexpected. One last comment about this slide and this exponential fit. Many of you know that the tunneling current of the STM is also, it rises exponentially. Well, this particular phenomenon, this dissipated energy here, that rises over 10 times sharper than the tunneling current of the STM. So it's a very, very short range interaction. Okay. With that, I'm going to kind of slowly wrap up here. I just want to say you can read about this work. We published it last year in Physical Review Letters about strumming a single chemical bond. I think it's really a lot of fun what we're now able to do with these with this lateral force microscopy, where we really try to control the tip. It always surprises me that more groups around the world don't pursue something very similar, but okay, as far as I know, we're the only ones doing it. And so we do a lot of work. We establish LFM as a technique where we try to make ways to determine the amplitude of oscillation. I talked a bit about the sensor tilt, how to extract useful physical parameters from our observations. And then we take a lot of fun measurements. So the latest one actually we had was this year, where we looked at a molecular switch with LFM. And of course, we're not stopping there. There's a lot of things that we're going to try now and in the future. So our outlook is we've got a collaboration with a theorist, Oliver Hoffman in Graz University, who performs DFT-based calculations. We're now expanding our model to allow CO relaxation in 2 dimensions. And from the experimental side, what I think is really exciting is that we're working towards simultaneously measuring both AFM and LFM with our very, very stiff sensor. We've already demonstrated that at room temperature measurements. You can read about that. That article came out this year. And this is going to allow us to also take a look at these lateral forces, the force of friction, as a function of the normal force, which is exactly what we learned in grade school, but we're going to do it at the atomic level. All right. And at that point, I'm at the end. I just want to say a big, big thank you to the scientific committee of this meeting for their very kind invitation, especially Sekand Ali Chitin. That was very, very nice of you. And I have to acknowledge the German Research Foundation's grant, which I won, which allowed us to do this work. Here's a photo of my co-authors from left to right. There's Franz Giesepel, there's Oliver Gretz, there's myself, and Elizabeth Riegel. So at this point, I thank you very much for your attention, and I would happily answer any questions now.
Okay, thank you very much, Professor Raymond. Question, please. If no questions, thanks once more. And I'll invite our next speaker, Professor Ali Yilmaz from NETU. The title of his talk, Student Achievement and Microconceptions in Physics, what they really mean and what we really measure. Please.
Okay, thank you. I want to share my screen with you. Okay. Can you see my screen right now?
No.
No. Sorry, but I have to quit and reopen the Zoom. Sorry about that. Yeah, hopefully I can do it right now. Yeah, it's there. Yeah, can you see my screen right now?
Yes.
Okay, sorry for the inconvenience. Let me. Yeah, my name is Ali Yilmaz, and my major is physics education from Middle East Technical University. Today, I'm going to talk about the students' achievement and misconceptions in physics and what they are really mean and what we really measure. But before that, I want to mention my previous talk in 2017, TPS13, what we teach, what is learned, closing the gap. And in that talk, I can summarize it. The students come to the class with the common sense concept about the real life. And this common sense is, most of the common sense, they are misconceptions. And these misconceptions come collectively from students' daily life experiences, textbooks, and even from instruction. It means actually instructor. And these misconceptions are resistant to change by conventional instruction, but if you properly arrange the curriculum, you can remediate these misconceptions. And I want to add this last summary for my previous talk. These students' misconceptions are one of the important factors that affect students' achievement in physics. Therefore, my presentation today is going to relate to what the students' achievement and misconceptions, what they are really are, and how to assess them. I want to compare the achievement and misconceptions test. I'm not going to go detail, but actually this is the kind of summary of my presentation. Like the difference is the like scoring given to the correct answer in the achievement test, but for the misconception test, we can give score to correct answer as well as the misconception alternatives. For the table of specification in the achievement test, we use objective categorized by taxonomy. Most of the time is the Bloom taxonomy. But for the misconception test, we use misconception list as a table of test specification. And for the reliability, we are going to go detail in the reliability, but most of the time what we can say, the reliability of the achievement test is greater than the reliability of the misconception test. What is achievement? Most of the time, what we mean by the achievement differs actually. And underneath of the achievement, what we can say is the students' learning outcomes. And when you categorize the student learning outcomes, we have 3 domains: cognitive, affective, and psychomotor domains. And actually, the achievement consists of these 3 domains. What happens, we only measure, when we measure the achievement, we only measure cognitive domain, not the affective and psychomotor domains. And in the cognitive domain, like this is the Bloom taxonomy of the cognitive domain, what we do usually, we only measure the lowest, the simplest part of the cognitive domain, like remembering, understanding, and applying. We don't go the upper levels, analyze, evaluate, or the create level. What kind of questions we use for the achievement and misconception test? As you see, we have some of them here. Which one is the best? None of them is the best, actually. We can use all of them according to our intent, according to our aim. But what we do, like if you want to measure the highest part of the cognitive domain, you can use essay types. You want to use the reliable items, then you can use objective test items like multiple choice questions, true, false, matching. I want to concentrate on the multiple choice test in this presentation. Why? Because it's objective test item, first of all. Plus, if the number of participants is too large, multiple choice questions can be usable, feasible to use. Plus, for this range, by using multiple choice questions, we can go up to analyze level, from remembering to analyze level, including the analyze level, we can measure actually. Although the use of multiple choice question is very common, there are some critics in the literature about the multiple choice question, and some of them is what it really measures because it is objective test item and all the alternatives are given to the students. and by only one item, it's really hard to determine what it really measures. Therefore, what is the solution? In the literature, they say that we can use 3-tier questions. False positive and false negative and lack of knowledge is the other critics for the conventional multiple choice questions, because there is no tool to calculate false positive, false negative, and lack of knowledge percentages. And the last thing, as I told, like in the case of the alternative, if the alternatives are not feasible, are not meaningful to the students, it is really hard to determine what it really measures. Therefore, the solution for this, they say you can add a blank alternative for multiple choice questions. I'm going to introduce you to 3-tier questions later on in this presentation, but before that, I want to talk a little bit about the reliability. And we know that actually for the any physical quantities, when we try to measure them, these are my real mass and length right now. And we know that there is a tolerance there depending on the tool we are measuring. That tolerance, that standard error of the measurement changes, as you see, for mass and length. But what happens for the electron, for example, it's very electron mass. It is very small value, as you see, 10 to the power minus 31 kilograms. And most of the time, we don't talk about that tolerance value for these small values, but we have it. What about electric charge? Even if it is too small, again, we have it. But what about students' achievement and misconceptions? We give a test to the students and we score it out of 100 and we say that, okay, you get a 60. Or we have a misconception test and we gave it to the students and we say, okay, you got a 60. Is that it? What is the standard of the measurement? How big it is? Of course, it's going to depend on the measuring tool we are going to use. But if we categorize the measuring tools, what we have a standardized test, like PISA test, like TEAMS test, and we have other tests, teacher-developed test, researcher-developed test. And this table is summarized that, like, as I told you, the reliability of achievement tests are usually greater than the misconceptions, and the reliability of the achievement test for the researcher-developed is approximately 0.8, and for the standard test, it is for 0.9. And if you compare the misconception tests, 0.6 and 0.7, as you see, reliability of the achievement test is greater than the reliability of the misconception test. But if you compare the standard error, if the test is researcher developed or the instructor developed, professor developed, the standard error of the measurement is 20% out of 100. If it is standardized, but we don't use in schools, we don't use standardized tests, most of the time it is 20. What about the misconception test? It is 40%. Standard error of the measurement is 40%. Therefore, do we have the tolerance value for the achievement and misconception? Yeah, of course. If it is 60, the student score on the exam is 60, the true score of that student, if it is researcher developed, the instructor developed, the true score must be between 40 to 80. If it is misconception test, and if the student score is 60, as you see here, the true score of the students between 20 to 100. It covers almost the whole possible range. Our error rate is too much for the achievement and misconception scores. It is not like the physical quantities. Then what we are going to do? We want to increase the reliability, decrease the standard error of the measurement. How? By using objective test items, first of all, instead of essay type items. We want to use more questions in a specific test. Most of the time, what happens, especially in the universities, they use only essay type questions and very limited questions, like 2 questions, 3 questions, 4 questions. And reliability of that test is too low, actually. Means standard error of the measurement for that test is too high. We cannot discriminate students by using that measuring tool. What next? We have to increase number of measurements. Means they have to give assignment, projects, number of midterms, laboratories, and other observations. I want to introduce you to three-tier misconception question. As you see, we have 3 questions here. 1, 1, 1. But the first tier of this question is normal conventional multiple choice question. And in this first question, the concept of problem is asked. That's normal conventional multiple choice question. But in the second tier, we ask the reason of the first question. And for the third tier, we ask to what extent the student is sure about his or her answer. Let me give an example for that. You see, very simple question. It's a kind of multiple choice, but we have a battery, we have a bulb, we have a wire, and the question, does the bulb in the figure light up? We all know that this bulb is not going to light up. We know it. And assume that the student's answer B, no, it doesn't. Is the answer is correct? Assume that the student says that in the second answer, we ask the reason of the first question, it says, yeah, B, the bulb does not light up. Then it says, yeah, why it does not light up? Because you put the wire to the wrong pole of the battery. You have to put that wire to the negative pole of the battery. Then the first answer is correct or not? What happens if the students choose C here? It says that, okay, you need another wire from the negative battery, but from the negative pole of the battery, the electrons comes from the positive charges comes, and they collide on the bulb, and then it lights up. Is the correct answer? Even if it say it does not light up. Therefore, the second tier of the question is really important because it asks the reason why it is yes or no. And the third is very easy, whether the students, they are sure about their answers, the previous 2 answers, sure or not sure. Again, the common wrong assumption is most of the time we use misconception score as the reverse of the achievement score. We say that if you 100 minus achievement score, we end up with the misconception score. Is this correct? No, this is not correct. Check this answer, check this table. If the student is sure about his responses, then this table comes up. If the student is not sure about his answers, what happens? We can categorize the students as lack of knowledge. The student does not know. Even if his answer is correct or wrong, no problem. Even if it's a misconception, if the student says that I am not sure about my answer, we can categorize the students as a lack of knowledge. But student says, yeah, I am sure about my knowledge. Then we have 4 different options because we have the result of the first tier and result of the second tier, as you see from here. If the first tier is correct and the second tier is correct, we have the knowledge of the correct response. This is the achievement part. What about both of them is wrong here, as you see this part. First tier is wrong, second tier is wrong, but they are parallel, they are consistent to each other. The logic is the same. Then we can categorize them mostly misconception, and some of them it could be a mistake, of course. And you know, we have a false negative means the first tier is false and second tier is correct. We call it false negative. And we have a false positive If the first tier is correct and second tier is wrong, then we call it positive, false positive. But sometimes we have rare misconceptions, as you see from the previous example. Even if the students choose B here, and by itself it seems correct, but if the students comes here and choose B and C, actually students have a misconception there. Therefore, even if the answer in the normal conventional multiple choice question seems correct, when you use the three-tier multiple choice questions, you can see whether it is a misconception, is a correct conception, whether it's a false negative, is a false positive, or whether it's the lack of knowledge or not. Then I ask the same question again. Can we say that misconception score is the 100 minus the achievement score? No, it is not correct. Therefore, you have to develop a test to assess achievement score, achievement and the misconception separately, and you have to code it differently. In order to explain this, I want to give an example from my study, but before that, I want to explain some more, like there are some critics, some problems related with the three-tier test. Actually, these are not related with the three-tier test, but they are related with the use of three-tier tests, like factor analysis. Factor analysis is really important for the measuring tools for the achievement and misconception test. Why? Because they construct the related evidence of the test. And by using the three-tier test, test, you reduce the reliability most of the time. Why? Because you decrease the standard deviation, because you recode 3 questions as if they are 1 question. You code the first tier as 1, second tier 1, and third tier 1 or 0. Then as a whole, you give 1 if all of them is 1. Therefore, you decrease the standard deviation and results in low reliability. In what happens in the misconception test, they want to measure a lot of misconceptions by using very low number of misconception questions. And this is another problem. This is the summary of the lit review, actually, and I want to give an example how to solve this problem by using my study, and the study is here. I want to develop a 3-tier test to measure students' misconceptions about heat and temperature. By using this test, I want to assess Turkish bachelor, master, PhD students' misconceptions by new oncoming style, coding style. And these are the misconceptions that I measured. Heat and temperature are the same. Temperature is a measure of it. Heat and temperature are not the same, but they can be used interchangeably in the context. Or the last misconception, the temperature of the desks resting in a room for a long time depends on their sizes and or their materials. I want to show you my test. Can you see the test? Okay, we have actually 2 questions here, 2 contexts here. One of them is we have 2 desks made by the same material, iron, but different size. The other question is here, we have the same size table here, but made up of different material. Then we ask the same questions, like compare their temperature, their reason, to what extent you are sure about the answer. And the same questions, actually, we are comparing their heat here, their reason, and to what extent they are sure about it. And same things happen here, but right now we have same size table, different material, and again, compares the temperature and compares the heat of the tables. And the last question summarizes the relationship between the heat and temperature here. What happens here? We can code this question, as I told you, 101010 differently, but these are actually one question, 1112 and 13. They are the one question. Therefore, to code them as a three-tier question, if all of them 1, we score it as 1. Otherwise, we score it 0. But this is the normal, this is the conventional coding of the three-tier multiple choice questions. But what we did in this question, actually, we score it to row wise. How? Because it compares the temperature with the heat, and even the alternatives are the same. It says small table have higher temperature, small table have higher heat. Large table have higher temperature, large table have higher heat, as you see. Therefore, we coded the row wise. And if the student choose A and A here, we say that, okay, students confuse temperature with the heat. Therefore, we code it as 1 when the students choose A and A there. Let me go back to my presentation again. That was the test. And this is the development of the test. The data, we put our test to the web. Therefore, it was open to everybody. More than 3,000 participants, they filled the test. And we are going to concentrate on the bachelor, master, PhD students here. And as you see, we have more than 1,600 bachelors, students or graduates, and more than 800, they are students, like approximately 400, they are teachers. We have engineers, officers, and others. For the master students or graduates, we have teachers, we have research assistants, PhD students or graduates, we have academicians, students, physicians, and teachers. This is the coding for the correct score of the test, because we can use the same test as an achievement test as well as misconception test. If you want to use the same test with the achievement test, we can score it for the correct scores. And this is the answer. For the question 1.1, C is the correct answer. Again, the same 1.1, D in small d is the answer. Capital C is the answer. And this is the answer for the correct score. And this is the coding for a specific misconception, and that misconception is the heat and temperature are the same misconception as you see. As you see, we have different or and bulletins. We collect them, and when all of them is the correct, then we give 1, otherwise we give 0 to students. And this is the sum part of the result. These are the temperature 1112, temperature 2122 questions. These are the heat. And this is the last question, as you see. And this is the percentage of the correct. It starts from like the most highest one is 78, as you see. For it comes from the master students. The lowest one is the 6%, and it's related with the heat questions. And it comes from the bachelor, but as you see, heat percentages are really low. But if you quote as the first 2 tiers, as you see, the percentages drop down. And if you quote all 3 tiers as a one question, and percentages dropped lower, even lower, as you see. Let me go. For the false positive, false negatives, now we have, because we have 3 tiers, we are able to calculate false positive, negatives, and lack of knowledge by using that table I showed you. And these are the percentages, as you see. Usually false positive is larger than false negative. And as an average here, 5.8 to 6.83, as you see here. And lack of knowledge, approximately it is 10. Let me go further. Yeah. This is for the misconception, and the same misconception for the first tiers. Misconception is like 16% for the first tiers for the question 1. For the question 2, it's 34% for the bachelors and the others, as you see there. The or and is really kind of complex right now. I don't want to go in that detail. And by using the factor analysis, this is the factor analysis results. And as you see, if you choose the 5 misconceptions or the 4 misconceptions, we have 2 factors. And this is the reliability, and this is the percentage of these are the percentage of the explained variance by the 2 factors. The reliability, the smallest reliability is 0.69, as you see, and the highest one for like 0.86. And for the misconception test, these values are really high values. And as you see here, for the PhD students, even if you take the 5 misconceptions or 4 misconceptions, we have only 1 factor. This means that we have 1 unitary concept for the heat and temperature. 1 unitary concept. Okay, I'm concluding. This is my conclusion. The blank alternative worked very nicely. We should use 3-tier questions for to measure achievement as well as misconception. And by using that, we are able to calculate false positive, false negative, and lack of knowledge. And we have to interpret these values to assess students' achievement and misconceptions. Of course, the different coding should be used for misconceptions course, misconception test, as well as for the achievement test. And the total score for the misconception test is not that meaningful. We have to calculate total score for each misconception. This was an example for the heat and temperature. We have different PhD theses and master thesis in Middle East Technical University. All of them, I was the supervisor for all of them. Like this is for geometrical optics. And as you see, right now we have 4-tier tests. It was 3-tier test at that time, but right now we have 4-tier test. And we have simple electric circuits, kinematic graphs, optics again, simple electric circuits, and for force and motion. I think, yeah.
Okay, thank you very much for your very interesting talk. Questions, please.
Yes. So, were these questions asked in English or in Turkish?
It was in Turkish, of course, yeah, because we applied in Turkish, yeah.
Okay. So thank you very much once more. And we have break 15 minutes. After break, we continue our work in this session.
O zaman şöyle diyelim, projede yapacağımız fotodedektörde için düşük akım ve ortak değerleri yeterlidir. Değerleri yeterlidir. Yüksek fotovoltaik verme gerek yoktur diyelim. Ya da aynen daha güzel. Sektörler ne diyelim, düşük akma voltaj değerlerinde çalışabilirsek küçük fotodedektörler için yüksek bunlar güneş pili değillerdi. Fotodedektörler güneş pili olmadığı için onunla belki güneş pili olmadıkları için verimlerinin yüksek olmasına gerek yoktur. Güneş pili olmadıkları için evet, daha da doğru. Güneş pilleri olarak kullanılmadığı için ya da güneş pili olarak kullanılmadığı için.
Okay, I think that we can start. Our next speaker is Professor Fahrettin Yapanoğlu. Title of his talk is Organic Radar Absorption Materials for Steel Technology. You have 30 minutes, please. You can start.
Okay, thank you. Now I want to share my presentation, but I think the sharing hot disabled now. Are you hear me?
I'm hearing very well you.
Yes.
I can hear you, Fahrettin.
Okay. Now, select all. Okay. Now. Notice here. Okay, now I share.
Yes,
It's okay now?
yes, yes.
Okay. Okay. Good morning, everybody. My name is Fahrettin Yakupanoğlu from the Fırat University. Today, I want to talk about the organic radar absorbing materials. absorbing materials also wait. Slide. Okay, now I think. Okay, yes. Rather organic radar absorption materials, as you know, the steel technology is very important for the military application. So we want to prepare the new radar absorption materials using the organic materials. As you know, the radar absorbing materials may be classified as magnetic, dielectric, or hybrid combination of the magnetic F dielectric materials. Such classification is done according to the wave material interaction mechanism. Regarding the type of the absorbance center using in the absorber process, these called absorber center are additives with the characteristic cause the attenuation of the radiation, maybe carbon particle in conducting polymer, the other inorganic materials. Due to the rather interesting behavior of the conducting polymers, especially the polyaniline, regarding modulation, the intrinsic electrical conductivity. This dopant has been used as microwave radiation absorption center. Also, the radar absorption materials in addition to their application in aircraft, making them less susceptible to radar, are not restricted to this field. The RAM also enable the protection of the communication and safety system employed in aircraft, in ships, in automobile. Therefore, these materials have became the important topic of the research development in recent years. For the proposed reduction of eliminated the presence of the surface radiation in the environment caused the big great variety of the electronic equipment, especially the employing the high frequency. Thus, the research the new materials to be used in shielding of electronic equipment against the electromagnetic interference and reduction by the radar detection has become essential and strategic for the country. However, there is an evident restriction in accessing technology considering the strategic, for example, including the component using the process of the aircraft related to the space and defense area. Okay, also now in recent years, there are many studies on the organic materials, rather absorbing materials using the military. With this idea, due to the need to dominate and nationalize the technology for the formulating materials with the radiation absorption characteristic in certain wavelengths. The wavelengths. So our aim is to synthesize new radar absorption materials. Now, as you know, the many countries has the special radar absorption materials. Just what are the different these materials? Only the frequency, reflectance frequency is different. So we need the new type materials, new type radar absorption materials. Also, as you know, the organic materials, the first organic materials, I think in 2000 years, Alan G. Eager, he discovered the polymer, discovered the semiconducting polymer. Then the semiconducting polymer find the find the application opportunity for the different technology. Now you know the steel technology is very important technology in the military. Okay, what is the radar absorption materials? Why important? Since the radar was invented, the different technology has been used to minimize detection. There are some way to achieve the vessel shape, radar absorption materials. Also, the working frequency is very important. Also, most of the country use the as specific absorption materials. So also our country, we need the new materials with the new electromagnetic shielding parameters. Now you can see here the mechanism of the radar absorption materials is not more important. I think most of you know this mechanism. Also, the steel which shape and design is very important. The radar absorption materials should be coating for the radar detection. The radar absorption material should be coated with accurate angle. Also, you can use the planes on the wing at a certain angle. This is very important. Also, designs of the noise is very important. Now you can see here designs in very important. So for the radar absorption materials, you don't need them coated all of surface of the aircraft. You can use at a certain position of the aircraft. Now also you see now many researchers synthesize the new type radar absorption materials. Why we prefer the organic materials? As you know, the organic materials coating, it is easy. The preparation is easy. Also, the controlling of the thickness is easy. Also, you can change the electrical, magnetic, and optical parameters of the organic materials. There are now for the radar absorption materials, there are three components. The first one, electrical parameters, and second and magnetic parameters, and the other one insulator parameters. Very important to prepare high efficiency radar absorption materials. Now you can see here we prepare the nano composite organic materials. Organic material using the nano materials production system. They use the materials are polyaniline and graphene prepared. Now you can see here the scanning electron microscopy of the polyaniline and graphene nanocomposite and exfoliated the graphene. Now you see the structural morphology is changed depend on the composition of the composite. Also, how can we prepare the radar absorption materials? Radar absorption materials you can prepare as a paint. Also, you can coat it any substrate, and then you can use them in your aircraft. Now you can see here how we prepare the radar absorbing materials. For this you need the different flank. Now you can see here this is the Q band. For the X band there are different size. Okay, now you can see here the doped polyaniline graphene and the d-doped graphene doped the polyaniline graphene nanocomposite. You can see here when we dope it, the structure is changed. Also, Then we prepare the we prepare the rudder absorption material in different flank, and then we measure the reflectance versus the frequency. The frequency range is very important for the application. Now most of the country use the frequency range from the 8 gigahertz to 11 gigahertz. If you want to detect, for example, I quoted this material in our aircraft, and then if you want to detect to me, you send me one radar signal. If your frequency between the 8 gigahertz and 12 gigahertz, it is easy to can detect any aircraft. But for the if you don't detect it, you should automatically change your frequency. Here you can see here the frequency is changed. The space depend on the spacer. You see this is the resonance frequency for the different spacer. Also, another important parameters, dielectrical constant. As you know, the dielectric constant has the real part and imaginary part. Imaginary part and real part is related rather absorption reflectance parameter. Also, you can, if you want to control of the electrical parameters of RAM, you need to also change the dielectrical parameters. Dielectric parameters mean the real part and imaginary part. Real part and imaginary part is very important for the radar absorption material application. So now you can see here we measure from the 2 gigahertz to 18 gigahertz. This range very important. Why important? If we synthesize new radar frequency changeable materials, it's very important for the high technology application. For example, now any data want to detect you, they send you one signal. When this electromagnetic wave, you take this electromagnetic wave, your system automatically should change the frequency. Then the device cannot detect to you. Frequency range is very important. Now many countries work between the 8 and 12 gigahertz. Now we need to extend this range. If we extend this range, also is we find a special frequency, and then any radar, any device cannot detect our aircraft. Also, we need the variable frequency change RAM. Variable frequency RAM is the automatically change the frequency. When you system automatically, if they change the frequency, the radar cannot detect to your aircraft, your any device. You can see here the dielectrical parameters is very important. Parameters for the radar absorption application. If you want to analyze in detail the radar absorption materials, also you should measure the dielectric parameters. Also AC electrical conductivity is very important. Also now you can see here that we measure them and then we simulate the reflection from the design structure. Also we make some theoretical study on these materials. Now you can see here we can see here the sorry. Okay, now you can see here the variation reflection with the depend the different parameter. Also depend on the layer conductivity, also thickness, thickness also is very important for the radar absorption materials. Also, electrical conductivity is very important. If you want to change the electrical conductivity or the of the organic materials, you can use another. You can use, for example, the electrical conducting component. Electrical conducting component means the conducting materials. Then you can increase the electrical conductivity of the organic materials. Okay, how can we increase? You can prepare your sample in the composite form. Also, you can increase the electrical conductivity according to dopant content. Then you try to find the optimum parameters. Your radar absorption materials. This is very important. Also, you can prepare this material in the paint. In the paint also, the application is very easy. Also, we measure the reflectance at a different angle. Now you see, if to change the angle, the positive resonance frequency, positive reflectance, loss frequency is changed. You can see here. And now here for the 0 theta and then 20, and then we measure the different at a different angle. The angle also is important for the transparent electrical mode. So we also measure the reflectance in transparent magnetic mode. Also, magnetic mode very important for the application. Now you can see here. We measure them. Now we measure for the different angle. You can see here the angle is changed. The reflectance is changed by the theta. We need to find the optimum loss frequency. Optimum loss frequency for is important parameter for the RAM materials. Also, you can see here we compare the electric and transfer electric and magnetic mode. Now you see at low angle, the magnitude are the same. After when you increase the theta, you see the magnetic and electrical mode is effective in the different angle. So for the radar absorption application, also you should select the optimum theta. Theta is very important. This measurement of performance and 11 gigahertz. Also, then we want to measure the power density distribution of the structure. Now you can see here, we measure the different 8 gigahertz and 11 gigahertz and the different frequency. Now you can see here the power loss density distribution is depend on the frequency. Now you needed the unique parameter of the radar absorption materials is the frequency. Frequency is very important. Very important for them. For now development country has the special radar absorption materials. Also, their materials has the unique frequency. Anyone don't know the frequency of the radar absorption materials used in their aircraft in the other application. So we needed to find the specific frequency. Also, one thing very important thing, the power loss density distribution also is important. That application frequency That's the application frequency. So if you want to also, for example, you synthesize any other absorption materials. After the characterization, also you should determine the power law density distribution. Power law density distribution was very important for your materials. Then you should make the analyze. For example, your loss frequency, for example, 11 gigahertz. Also, you should make this tested the depth frequency. What is the, you should see the distribution of power loss density at that frequency. Also, now H magnetic distribution of the structure. Also, again, we measure the different gigahertz. You can see here that this distribution is depend on the frequency range, the reflection loss frequency. Now you can see here that we measure the 8, 11, and 14 gigahertz. Also, you see the magnetic distribution is changed by the frequency. Now, also, when you for example, when you prepare the new radar absorption materials, another important parameters, the electrical conductivity. Why electrical conductivity is important? Why electrical conductivity is important for the radar absorption mechanism? For example, if you want to prepare variable frequency radar absorption, when the radar attacked your radar RAM, your RAM should be automatically change the frequency. How it changed this frequency? As you know, when the electromagnetic wave how can I say, when you send the electromagnetic radiation on your radar absorption materials, the electric conductivity is changed. When your system understand now your electrical conductivity is changed, in that case, system automatically change the reflection loss frequency. In that case, radar cannot detect you. Also, for the next attack, again your system should change the frequency. So we need the current. So your radar absorption material should be homogeneous current distribution on the target. For example, now here I see them 11 gigahertz. Also, the current distribution is very important. This current distribution is very important for your materials. Now, if you want to synthesize, also mean to prepare the new radar absorption materials, first you should check the absorption spectra, the reflectance spectra, and transmittance spectra, and then also you should make the analyze the power density distribution. Also, current distribution is very important parameter for your materials. So, okay, now conclusion. I want to say, okay, all polymer on non-resonant wide band absorber a potential 3 printing is designed and fabricated. Here we use the plexiglass structure. Plexiglass structure contains the polyaniline and graphene composite graded with the conductivity, which act as an impedance transformer to guide the incident incident electromagnetic field. Here also we use the 5-layered polyaniline palette, has greater conductivity. Also we graded the thickness based on the golden ratio. The parameter has been optimized. We optimized parameters and then structure. Why we optimize it? We optimize it to the absorb the X band and the lower Q band. Its materials and microwave absorptive characteristics have quality in terms of the some analyze. The analyze we use the scanning electron microscopy, XRD analyzes, reflection loss. And then also we measure the power loss density and field distribution. Here the proposed design strategy offered two advantage. Over the conventional method. The first advantage of the all polymer absorption design, here also be specified here the white reduction that is achieved. White reduction is very also important, as metal are not used this design. Metal did not use it because we use the organic materials. All organic materials, the weight of the entire structure depend on the polymer. The polymer, which is light. The weight in comparison reduction the full requirement, and while this simultaneously the reduction rather entire system. Also, the second advantage of such polymer-based structure is the facile dopant manufacturing technology. That technology can be aid rapid generation complex shape to the suit target geometry. So I don't want to get more your time. Now I complete my presentation. Thanks for your attention.
Okay, thank you very much, Professor Yakupanoglu. Any question, please, if you have from participants. No question. Okay, thank you very much once more. And our next speaker is Christian Smora. The title of his talk is High Precision Measurements which Trapped Protons and Antiprotons.
So, hello, everyone. Can you hear and see me? Okay, I will take over the screen if I can. Just a second. So, yeah, so hello to the audience. It's a pity that I can't see you all due to this new remote concept of doing the presentations in the pandemic. So I'm here to speak about high precision measurements of single trapped antiprotons and protons. So we make here quite a switch in topic from stealth technology to particle physics. So, and the thing which we are trying to detect and with which is, let's say, concealed, that's the new physics that has been hiding from us since a long time. And we know that it must be there because we have to solve some puzzles like what is dark matter, or where does the baryon asymmetry in our universe come from. So I'm Christian Smorra. I work in Germany at the Institute of Physics in Mainz. Here you have a brief overview of the topics which I want to cover in my presentation in the next 25 minutes. So these measurements on single trap protons and antiprotons, they are conducted by the BASE collaboration, which has been formed at CERN in the year 2012. And at the moment, we are running 4 experiments that are dedicated to do these high precision proton-antiproton comparisons. We have experiments that are situated here in Mainz in Germany. That's where I am right now, where we have an apparatus to measure the proton magnetic moment, and where we currently implement sympathetic cooling methods of single trap protons. We are also building a transportable antiproton trap here in Mainz, which will be later moved to CERN. That's where the antiproton decelerator is, which is the world's only source for low energy antiprotons. And that's also where we have been conducting so far our antiproton precision measurements. Then we have an experiment in Hanover, which also develops future technology for us, quantum logic methods for our precision measurements. So why are we doing all of this, you may ask? So if you look in our universe and we look at our theory that we have, we see that there's a big contrast in our observations and our expectations. And I've tried to illustrate that here. So this is what we observe in the universe. And this here is what we expect if we use the standard model of particle physics and cosmology and try to predict the matter content that is in our universe. We end up with a number that's actually something like 10 orders of magnitude lower than what we actually observe. So I dare to say in this standard model universe, it would be pretty dark. And that's actually not due to dark matter. That would be here on the left side in the picture. So here we have just many photons at the wrong frequency, so we can't see them. Yes, so we have much more matter than we expect from the standard model. And we have much less antimatter in our universe than we would expect, because we have in principle a symmetry in theory between particles and antiparticles, and we expect in the Big Bang to have equal amounts of matter and antimatter, but we end up with very low fractional numbers of antimatter. If we look in our surroundings, for example, at cosmic rays or at gamma ray sources in the galactic disk, we find that there's not much antimatter there. So we ended up concluding that our theory is incomplete. And at the moment, we are really searching for the unknown. So we don't know which kind of new physics we are looking for. And experimentally, this requires a very diverse research program that we can cover all the potential candidates and parameters. So we have, for example, direct production of new particles at high energy. That is something you can do, for example, at the LHC. Or you can build low counting type experiments where you have a big detector with a very low background rate, and you try, for example, to detect a dark matter particle scattering in your detector. Or the third category, and that will be our focus in this presentation, that is precision measurements, where we try to reveal tiny deviations from the predictions of the standard model. One example for this type of experiment is, for example, this trap system which we have here at the University of Mainz, where we have a single trapped proton, and we try to measure its magnetic moment as precise as we can. So the single trapped proton or antiproton is confined in what we call a panning trap. So that's an ion trap that works with a magnetic field to confine the particle on a circular orbit. And then we have an electrode structure with an electric field that confines the particle along the magnetic field lines. And in this configuration, we can measure two frequencies of the trapped particle. One is the spin precession frequency, which we also call the Larmor frequency for the proton and the antiproton. And the second one is the cyclotron frequency of the particle in the magnetic field. So, and if we measure this, we end up, we can build frequency ratios, and that gives us the physical quantities which we are interested in. So for example, the antiproton magnetic moment is given by the ratio of the Larmor to cyclotron frequency. And if we measure this and we measure the same thing for the proton, we can test a prediction of the standard model, which says basically that the magnetic moments of proton and antiproton should be identical, except for the sign. So this is a way of searching for new physics in our experiments. And maybe once more, in general, what we are trying to do is we try to use a very well understood atomic system where we know the standard model Hamiltonian. For example, we would take the spin in the magnetic field, looking here at the proton-antiproton spin precession, and then we would try to detect a shift of the level spacing in our system, or we can even look for a dynamic change of the level frequency as a function of time. So it's compared, for example, to the high energy experiments. It's a very complementary way of searching for new physics. And if we look in particular at the antiproton measurements, so what could be this new physics, what we are looking for, this perturbance to our standard model Hamiltonian? So in general, you could think of new particles coupling through quantum field theory corrections to your system. And these would shift, for example, the magnetic moment of the particle that you're measuring. That would be one way to observe a coupling of a new particle to your system, and that would produce a tiny change in your level spacing. Okay, and if we look in particular at matter-antimatter comparisons, we can look for a breaking of CPT invariance. For example, if these couplings make a difference in the proton and antiproton magnetic moments. Okay. We can also look for, so these would be like static frequency shifts in our experiment. We can also have dynamic frequency shifts. One theory which describes that is the standard model extension, which is effective field theory that introduces Lorentz and CPT violation to the standard model. And so you can think of this extension like that you have a symmetry breaking field that points into a certain direction. And for example, if your experiment is aligned with this symmetry breaking field, you will measure a different frequency than, for example, when you're orthogonal, in orthogonal orientation to this field. Okay, and this third very interesting perspective is also, for example, that you measure, when you measure the frequency of your trapped particle, you also measure the gravitational redshift of that frequency due to the binding energy difference in the gravitational field. Okay, and if we, for example, measure our frequency for half a year, where we pass on here on this elliptic orbit. We move around the sun and we compare measurements from here to here. We could observe a difference in the gravitational redshift for the antiproton, and that would allow us to constrain that antimatter has an anomalous gravitational behavior. Okay, because this gravitational behavior is so far not known at all. So the antiproton experiments are done at CERN in Switzerland, where we have the antiproton decelerator, and that's a view into this facility. So we have here a synchrotron that's decelerating the antiprotons to an energy of about 5.3 MeV. And then since this year, we have also a second stage behind that, so a smaller synchrotron, which is called ELENA, that decelerates the antiproton to 100 keV. And then the beam is distributed to the various experiments in this facility, which work basically all on comparing matter and antimatter properties, or the antimatter gravity experiments. Okay, so I'm going to show here something about the base experiment, which has been running since about 2014 in this facility. And I will also talk about the antiproton transportable trap base step, where we've just received a new experiment area to commission this trap system at CERN in the coming years. So this year is how the trap system looks like, in which we do the antiproton precision measurements. It's a so this trap system is installed here in the bore of this superconducting magnet, and here the antiproton beam is coming from the left into this trap. And yeah, we confine here antiprotons in this trap system. We have this reservoir trap where we can confine the antiprotons that we catch from the injection. And then we can move single antiprotons out from this cloud of antiprotons into the other traps. And that's where we conduct the precision measurements, for example, on the antiproton magnetic moment or the antiproton charge to mass ratio. And what is very remarkable, that we can work with the system entirely non-destructively. So we detect the trapped particles due to their motion. They induce image currents in the electrodes, which are very tiny, but we can amplify and detect them and measure the particles and their oscillation frequency entirely non-destructively. Okay, and this enables us also then to store the antiprotons for a very long time. So we have a very good cryogenic vacuum in this trap chamber, which is hermetically closed when we do the measurements. And then we have a pressure of something like at least 10 to the minus 18 millibar or less. And this enables us to store antiprotons for more than a year. So here you see a plot of the number of confined antiprotons in this reservoir trap in the year 2016. And so we started with 18. We warmed our system up when we had only one antiproton left at the end of the year, and used about 17 particles for the precision measurements, which we've done in this trap system. Okay, so how do these precision measurements work? So we are interested in measuring these two frequencies, and we do that in a measurement trap where we have a very homogeneous magnetic field. And then one of the key techniques is that we apply a two-particle method, and we use multiple traps. And the idea is that you, for example, you're interested in the antiproton charge to mass ratio. So you will measure the cyclotron frequency in this measurement trap. And then when you've measured this frequency, you move the antiproton into another trap where you can store it while you measure with a second particle. In this case, we use a H- ion as a proxy for the proton. We move that into our measurement trap and then use this basically as a to calibrate the magnetic field. Yeah, so we want in the end a frequency ratio where the magnetic field cancels out, and and that's why basically we want to be very fast in exchanging these particles, that the magnetic field doesn't change between these two measurements. And the necessity that this magnetic field ratio cancels out is also, it's very important, and it's also yeah, it makes a limit on the precision which we can achieve if there are magnetic field fluctuations present during our measurements. We will see that if we look, when we look at the magnetic environment, we will see that this is very important. Okay, and in this way, we have essentially measured the proton magnetic moment. We have measured the proton and antiproton charge to mass ratios. And yeah, the antiproton magnetic moment for the first time with high precision at CERN, and a second measurement of the proton magnetic moment. And in this year, we are planning to publish a new result on the charge to mass ratio comparison of the proton and antiproton. So that's going to come soon, I hope. Okay, so here's a little overview of CPT invariance tests that have been done with antiparticles. So there were also other systems recently explored, for example, anti-hydrogen and light anti-nuclei. The base collaboration has made here its contribution to the antiproton charge to mass ratio, and in particular the antiproton magnetic moment measurement, which we improved, where we improved the limits by more than a factor of 1,000 to compare to what was previously available. What we've also done, but I don't have time to talk about this, is a study where we used this magnetic moment data to analyze the coupling of dark matter. So in particular, we used the axion model and looked at the coupling of the axions to the antiprotons. And to my knowledge, this was the first time that we've done a dark matter search with an antiparticle as detector. So, and there we've also published some limits. Okay, so here is the challenge that we are facing when we do these precision measurements in the AD ELENA facility. So here you see results from measuring the magnetic environment. So we place a magnetic field sensor near our trap system, and this is what we observe. And essentially what we see here are the magnetic field ramps from the synchrotron decelerating the antiprotons. If you look here at the numbers, so we have here frequency shifts of about 20 Hertz, and that's quite large. That's about 10 to the minus 6 in relative precision. But we want to measure something in the range that is, let's say, 10 to the minus 11 or even lower. So it's quite clear that this here will constitute a limit. And to work around this, what we've done so far is that we average our frequency measurements basically over one cycle of these magnetic field ramps, so that we have the same magnetic field fluctuations present in each of our frequency measurements. That helps us a little bit to average this effect out. And then, of course, we have magnetic shielding. But if we put all of these numbers into our favor, we end up with this red line here. And that So you see here the uncertainty of the cyclotron frequency ratio measurement. And the measurements we've done so far with antiprotons, you see that we've gotten better and better over time. But we are basically hitting now this limit. Okay, and what we've already done in one day where the facility was not operating, we managed to make a measurement with a proton, and we've shown that we can actually measure more precise when the magnetic field environment is calm. So the conclusion for us is that we want to relocate the antiproton measurements into a different facility where we have a calm magnetic field environment. Okay, and that's a bit challenging because we will need an open channel to our cryogenic trap system where we can bring the antiprotons in and out. And we have to make here a very careful design of this differential pumping system that basically forms this open channel to our trap system. So, and just to give you some numbers, at 10 to the minus 10 millibar pressure, we have about 5 seconds lifetime for the trapped antiprotons. So that means if we have 10 to the minus 10 here, we need a very big gradient in pressure. And we want to have here something like 10 to the minus 16 millibar in this cryogenic trap chamber to keep the antiprotons. Okay, so we have designed this trap system. It's currently being constructed and hopefully tested soon. If it works out, we can relocate our antiproton precision measurements into a calm magnetic environment, and eventually we may even expand the number of antiproton measurements beyond the space that is presently available in the AD and ELINA facility. So I think I'm running quite short on time, so I will skip a few more details on the transportable trap and switch to my last topic, which is the cooling of the proton and the antiproton. So, and this slide is here to say that it's very important for us to reach low temperatures. So in general, if you do an precision experiment in atomic physics, you want to have the temperature as low as possible because it will reduce your systematic shifts. For us, it's even more important because the magnetic moment measurements depend on having a particle with a very low cyclotron energy, because that's needed to distinguish the spin state of the antiproton. We need to distinguish between spin up and spin down in order to observe the spin flips, and that's an essential requirement for these measurements. Okay, I haven't explained this technique in detail, but so this is just to illustrate that we require this low temperature, and usually we have to work with resistive cooling to cool the antiproton. So we have to work, for example, with a 12 Kelvin resistor. We want to set the energy of the cyclotron mode to below 0.1 Kelvin. And that requires many, many attempts, and it's just too slow to practically work with that. At least if we want to improve the precision beyond what we have now. So our usual cooling method is resistive cooling that works approximately at the cryogenic environment temperature. Let's say it's 4.2 Kelvin. The advantage is that we can apply it to all trapped charged particles. Okay. We have, of course, better cooling methods. So we can do direct laser cooling, and it has been shown that you can cool particles to the motional ground state of the trap with this technique. The downside is you require a closed laser cooling cycle, and you need a an ion with suitable transition frequencies. And these here are the favorite ions that you would use in your penning trap system. Our favorite is the beryllium ion here, because it's very close in mass to the proton and the antiproton. Okay, then you can, of course, do sympathetic laser cooling. That means that you co-trap such an ion with your ion of interest, but then you need a particle with the same charge and a similar charge to mass ratio to cool this efficiently. And if you now think about this and you want to do it with an antiproton, you would need a negative ion. And there's so far laser cooling of negative ions has not been really very successful. So the question is, can we have something that is like direct laser cooling? We reach very low temperatures, but we can apply it to all trapped charged particles. So that's what we want. And there has been an idea that was proposed by Heinzen and Weinland long time ago, that you make the two ions interact via image currents. So you take your ion of interest, the proton, we take the laser cooled beryllium ion, and we add a coupling force basically by connecting two electrodes of the traps together electrically. And then we can exchange energy between these two trapped ions. And then if we apply laser cooling, so here we start with the hot proton and with the cold beryllium ion. And when we've approximately transferred all the energy to the beryllium ion, we shoot the laser and remove the energy from the beryllium ion. And then you can see that we have much less energy in the system. So that's kind of the idea of what we want to do. But it's very challenging if you look at the experimental parameters of our trap system. Essentially, the problem is that this image current is very small. Yeah, it's a few femtoamperes. Okay, and in our first demonstration, which has succeeded where we succeeded very recently, and you can tell that by the mask here, we have amplified these image currents with an LC circuit, and that allowed us to make this energy transfer happen and reach about 85% of the environment temperature with a single trap proton, and we've transmitted the laser cooling power through this LC circuit into the other trap. And you see basically that we can reduce the temperature by adding more beryllium ions into the second trap. So this axis here shows you essentially the number of trapped beryllium ions. Okay, and we are also working on making the protons even colder. We've reached something like 2 Kelvin so far, but we want to go even lower into the millikelvin regime. And therefore we have here this trap system where we want to do the energy exchange without LC circuit, because the noise of the LC circuit is basically preventing us from reaching these very low temperatures. And we've done some simulation studies that show that this is possible using a pulsed laser scheme. And hopefully we will be able to implement these techniques in the next 6 to 12 months, let's say. Okay, good. With this, I want to thank you for your attention. And that's the end of my talk.
Okay, thank you very much for your very nice, exciting talk. Questions, please.
I have no question. I just say that that's impressive results.
Many thanks. That's appreciated. Yeah, it's
Okay.
good.
No any extra questions, so I'd like to thank once more for your very nice talk. So our next speaker, Professor Lewis Kress, and the title of his talk, Nuclear Physics for Astrophysics with Small and Large Accelerator.
Yeah. Hello, everybody. I need to start by saying thanks to the organizers for inviting me here. I'm not so sure what is the format of this session. I presume it is a hybrid one with several online participants, but with many more on in a conference hall. And therefore, I say hello to everybody. I'm glad to be here. I'm Liviu Strache from the Institute for Physics and Nuclear Engineering, Horia Hulubei from Bucharest, Magurele. And I'm going to talk about nuclear physics for astrophysics using small and large accelerators. Let me see how I get to advance my my slides. Well, it's clearly, if I say astrophysics is somehow related to star physics, but what is it? I mean, nuclear astrophysics more recently, let's say, is becoming broader in its accept. And then it's nuclear physics for astrophysics, in particular, star dynamics, nucleosynthesis modeling, some specific observations also, space and gamma rays and X-rays observation, cosmochemistry of meteorites, and a few others more. Nuclear astrophysics. So I'm going to say a few words about how I conceived this presentation, because my understanding, it is not for a specialist, but is for a broader audience. I mean, physicists, of course, specialists, but not in this particular field. So I'll try to be, let's say, rather informative than to try to explain or go in detail into some topics. So I was putting here a few words on this slide about the fact that nuclear astrophysics, it was becoming an important motivation for all nuclear physics research, either small or large accelerators, for the reasons very clear that the nuclei and the nuclear reactions are not only the fuel of the stars, but also the origin of chemical elements. And then also, in many cases, elemental and isotopic abundances are the indelible fingerprints of the cosmic process. There are some early big successes of the nuclear astrophysics, and that essentially is the fact that it could explain the Big Bang nucleosynthesis, in the very few minutes after the original explosions. Nucleosynthesis that stopped at maximum, let's say, as lithium, and but then we can get a quantitative description of this Big Bang nucleosynthesis without parameter-free, or essentially at the very beginning determining some parameters like the first determination of the baryon to photon ratio, this 6 10 to minus 10, and then the number of neutrinos. And then also we have this this observation that clear that the nucleosynthesis is an ongoing process, and then the fact that we could and we can explain very well the pretty much the reactions in the sun, which is, yes, seeing from the middle of the galaxy is one peripheral star, but for us is the most important one. And then we know that after the Big Bang nucleosynthesis, we have stellar nucleosynthesis, which started like a few hundred a million years after the original explosion, when the interstellar gas by gravitational contraction gave birth to stars. Further gravitational contractions led to thermonuclear reactions, to high temperature thermonuclear reaction, explosions, and then elemental mixing after these explosions because the cycle repeated. And what we are looking at to explain the elemental formation in the universe is to look at fingerprints like this solar system abundance, and then also at abundances that were more recently observed in different stars or different galaxies, far or closer from where we are. And from the point of view of a nuclear physicist, which I am, what we need is nuclear data to explain the structure, which is clearly not a simple one of these abundances. And then the basic one for the nuclear physicist is that the problem is that in stars we have distributions of energies, relative energies between the components, and then if the two partners in the nuclear reactions are charged, there is a strong Coulomb barrier that prevents them, and only quantum mechanics and the penetration through barrier makes them possible. And then from the fact that we have such a dependence and exponential decrease of the abundance in the Maxwell-Boltzmann distribution, then we have in the other direction, the increase of the cross section gives us what you call the Gamow peak, and this is where this is the region where the reactions are important and where we need to. But the very big problem is the stars are cold compared to the energies that are typically in the nuclear laboratories, which are 1 MeV, 10 MeV, 100 MeV, eventually per nucleon. The stars are very cold. They have their reaction happened in the tens to hundreds kilo electron volts. Therefore, we get to do nuclear physics for astrophysics basically in two ways. Either do reaction direct measurements, which means exactly the reaction that happens in the stars at the low energies that they happen in the star, or very close to that, and then extrapolations, which can be guided or not by theory. These are difficult because they're extremely low cross sections. They are, if cross section in the nuclear field, the typical one is maybe go close to 1 bar. There are reactions that have cross sections of pico and femto barns. And yes, there is a number of a limited combination of stable beams and target, whereas we know that there are tens of thousands of nuclear reactions that happen, and most of them happen in the region where the nuclei are unstable. We need special accelerator with special detection conditions. But then we can use indirect methods where we make measurements at energies where are more comfortable, like 10 times up to 1,000 times more energetic. But then we need to select the quantities that we measure and transform that basically into nuclear astrophysics reaction rates. One of the ways is to use radioactive ion beams. And then there are several methods like this. In particular, I'm going to talk only about those things that we do here in our institute at Magurele in the Department of Nuclear Physics. And then they're going to be into these categories. The direct measurement that we have with a 3 millivolt tandem accelerator. And then in particular, what we gain by going into an ultra low background laboratory in a salt mine, which is unfortunately about 120 kilometers away. And then also indirect measurements, but this we had to do at international facilities with radioactive beams because we do not have radioactive beams in Bucharest, or we don't have yet. The home infrastructure is listed here. We have 3 tandem accelerator. One is the 3 million tandetron, 3 million volts that I'm going to talk about because we used it. There is another one, an older one of 9 million volts, but it can also be used, and then a smaller one dedicated to accelerator mass spectrometry. I'm not going to use data from this. I'm going to show this is a picture of the accelerator. The accelerator is here, a Cockcroft-Walton type machine, and then 3 beam lines. We use the one farther in the back. This is it. Here it is relatively newly installed. And then the best results we got when we combined this machine with an ultra low background in a salt mine in Slanik Prahova. I mean, in this cathedral-like environment that you see on the right-hand side, it happens that there is a ultra low gamma ray background due to the very fact that these salt walls are very compact. There are no cracks through which radon, for example, can migrate from the walls of granite walls that are farther away. And then essentially what happens there, if you're measuring a spectrum like the green on top outside on the surface, and then you're measuring it down with some protection, with some shielding, you can get a factor of 4,000 reduction in the background, which is interesting. And then we had an experiment that took us a few years to finish with some collaborators from China, Institute of Modern Physics in Lanzhou, China. And then the motivation is one of the most important nuclear reactions in astrophysics, and namely carbon-12 plus carbon-12. That's very difficult to measure. The barrier is pretty high, but the so-called gamma window is under 2 MeV in the center of mass. And then on top of this, the reaction is very fluctuating due to some resonances that occur in this carbon-12 plus carbon-12. But then efforts were made to measure it, and then essentially we came with the idea that let's look into carbon-13 plus carbon-12 because no resonances are shown, and then one can see that adding 1 neutron avoids the resonance, the fluctuations that happen with the carbon-12 plus carbon-12. And then we can get the trend, how it works at the lower energies. And then we did this with this combination between the accelerator. And then one reason to do it is that there is one channel, one production by the evaporation of a proton from the compound nucleus that has a lifetime of 15 hours, which is enough for us to take the probes, which were irradiated typically for 1 day, and then to measure them for another day in the salt mine. And then you see one of the lowest energies actually is the second lowest energy. Then you see a spectrum, and then a spectrum with the background subtracted. We see very well the contribution from this sodium 24, which was produced in there. Therefore, we could measure the cross section very far down. We have improved the sensitivity to at least a factor of 100 from whatever could be measured best in all other laboratories around, and therefore try to give an answer to a question that was existing before. So how is the trend at very low energies of this cross section, actually plotting the astrophysical S factor, which was defined in one of the earlier. And then there was a model that is preferred by some of our colleagues, in particular a group at the Argonne National Laboratory, is called the hindrance model. But it's clearly shown that this hindrance model does not work. Our data is showing that we extend on this type of description of the plot, not on theirs. And therefore, this would be also what one can say about this carbon 12 plus carbon 12. It's it's more likely to go straight in this astrophysical S factor to continue at this constant value and not to go down very much as the others. Here I'm showing, well, there are some people that were contradicting this data. These data are also, let's say, ours, because I was participating in it as a publication in Nature with a method which is called the Trojan horse method. But then this depends on how you make the extrapolations of lower energies. And some people say, no, this is the way to extrapolate them, which doesn't, and there is a huge difference between this and this. And then we show that, no, this is not the right way to extrapolate them. It's a picture of the groups that we're working in here. So what can we do next? Well, I think next we can extend the understanding by studying the ion-ion fusion reaction mechanism at subbarrier energies, but for other combinations. For example, there are two other important ion-ion reactions in the stars: 12 carbon plus 16 oxygen, or 16 oxygen plus 16 oxygen. And we were trying to apply the same idea. However, here we missed the situation that the longest lived reaction product is like 9.5 minutes. It's no way to take it in the salt mine. Therefore, we had to invent something. We call it Bega station, from beta gamma station, where we make a coincidence between some scintillator, which is detecting betas, and the gamma ray detector, all shielded in a lab. That's a newer attempt to measure. Then we have only some preliminary results that show that, yes, we can work. However, here, the reduction of the background is so far only a factor of 80, not. Then talking about this work at home, as summary, we have this new 3MV Tandetron, which shows to be competitive for nuclear astrophysics for alpha and light ion-induced reactions. We got an excellent possibility for detection from activation using the ultra-low background laboratory in a salt mine. And when the lifetimes are not long enough, longer than 1-2 hours, we need to use these Bega stations. It's probably not difficult to understand that collaborations also lead to better science. We have other topics that can be attached of nuclear astrophysics that can be attacked at different other facilities that we have here in the same department. But then I want to tell you, and then some of the Turkish physicists know and use this, that our laboratory is an open science laboratory. And then we have even support for the outside groups that in the last time they got slightly more than half of the beam time at our accelerators. And let me go to the second part, which is the indirect method in nuclear astrophysics, where we make some measurements of lab energies. I said here 1 to 100 MeV per nucleon. And comparing with reaction calculation, we extract some nuclear structure information. And then from there, we evaluate the astrophysical important quantities. Of course, we should always compare with better data here, and then even compare with direct measurements in cases where they exist. And then we could only do this at outside facilities because it involved the radioactive bion beams. And one of them is the Coulomb nuclear breakup with carbon 9. in Japan at the RIBEF of RIKEN. And another topic that I'm going to show briefly is better delayed proton decay at Texas A&M. Why carbon-9 proton breakup? From the breakup of carbon-9, we can obtain information about the inverse reaction, namely of the radiative proton capture on boron-8. And then there are ideas that this reaction, proton on boron-8, may lead to trajectories to go to the formation of the metals going beyond or the triple alpha mechanism, which is the typical one that is supposed by other people. And the Coulomb dissociation is that the idea to use instead of radiative capture, to use the photo dissociation, and instead of photons, the real photons, to use the virtual ones, which are obtained by motion of the projectiles through a high field, in particular here in the field of lead target. Well, the nuclear breakup, it's on a different idea. Do the breakup in the field of low Z, the carbon in this reaction, in this our case, then also it's important to compare the two results. This is the schematic of the very large complex of the RIKEN at Waco in Japan, and currently is the largest facility for radioactive ion beams, but there are a few coming from behind. And then we use the so-called Samurai magnetic spectrometer. I'm not going to tell you details except to say that here in the green we put our targets, and we added an important detection system, silicon strip detector system, and then it has the peculiarity that due to the fact, to the quality, to the typically low quality of the radioactive ion beams, the beam gets to go through the detectors, and then there are 4 detectors here. And the basic thing is that they added 1,024 channels of data that we had to handle, and we could handle it. And then the results, the preliminary results, are shown here. One result is that we could reproduce the momentum distributions of the boron-8 after the carbon target, and then we are in agreement with what has been before measured in GSI, and then these are only preliminary results. To show you the complexity of the project is to show you, for example, how many people are involved, how many groups. Let me go to the second part. This is part of, let's say, the spectroscopy of resonances. In some cases, the radiative proton capture reactions are dominated by resonances. If you determine the resonance properties, I mean, like the location and then the width and the spin and parity, you can determine or evaluate the reaction rates. We did this using the Texas A&M beam. I worked at Texas A&M 20 years, and then I started this project there. The first thing was to use some silicon strip detectors. So the basic idea is the following. Yes, in the resonant capture, the direct, is you see that we have protons, and then if we're close to this metastable state, the rate is dominated by these properties. At the location, you see there is in the reaction rate intervenes the position of it, and then the so-called gamma strengths or resonance strengths. And then if you find these parameters from populating the same metastable states, like for example from the decay, beta decay of a nucleus that leads to the same compound system, you can solve the problem. And then the problems are that the proton energies are very important location, but then these proton energies are very, very small, and they are not easy to find. So the first step is to produce and separate the radioactive species, and we did it with the Mars separator, and then in particular here, let's say, is the 27 phosphorum. We were looking, then we implanted it in a very thin detector. The thinnest was 45 microns, and implanted here, it means that slowing it down from like a quarter of a speed of light, and then putting it exactly in the middle of this detector, and then we try to measure this is how it looks, and try to make a result. And then the thing is the following. Given that the fact that this radioactive, this proton decay, a very small in probability, 10 to minus 4, 10 to minus 5 of the total, always when you get a positron in that silicon detector gives you a background like this. And then the interesting part is in here, which you could not see. What you want to see is something like this. And then we could only do that if we, instead of using a silicon detector in which to implant our decaying exotic nuclei, we do it in gas. And then the gas, the positron leaves a smaller energy, a smaller signal. And then the other problem was that the protons you can detect, but the signal is weak, which we increase by using the so-called micromeso gas detector. There's something that you see here. Then it's based on the fact that it has an avalanche increase of the signal in very last 125 microns with a very small voltage, but a large field. That's a schematic of it, and then looking for the particular motivation for astrophysics is the formation and depletion of aluminum-24, which is being formed in this reaction, capture of proton on aluminum-26, which is studied by the decay of beta delayed proton emission from phosphor-27, and then the result is this one. You look, we see the background, it's lower than 100 keV, and then we see these tiny peaks, 263 keV, 461. But then this difference here of 200 keV gives in terms of solar, of contribution, not in solar, but in higher temperature, of 3-4 orders of magnitudes in favor of this particular state here. So maybe there is something else, 100 keV lower, but we don't know yet. I'm putting these numbers here to see that the branches are extremely low, 10 to minus 5 or 10 to minus 4. And then only the one that is confirmed as a new resonance gives you the largest contribution in function of the temperature in gigakelvin in here. There's another thing that we do in this small group that I have of young students in terms of nuclear astrophysics, we call ourselves Nuclear Astrophysics Group, is that we organized a number of events which are pretty well known, became pretty well known. And then I listed here a few that we organized in 2021. Namely, there were two online, including participation in Trento, this key reaction in nuclear astrophysics, but also more recently, because it happened, it only ended last week, is this Carpathian Summer School of Physics 2020. 2020 is like the Olympics that could not happen in 2020, but we had to do it in 2021. We dare to call people from all around the world. And I was thinking when I started that maybe 20, 30 people would do it, and then I will declare it a success. We had 81 in total. And I was very glad to hear that it was one of the first, if not the first, that happened in person after this. So with extra care, you see that we took the conditions. We respected the conditions for smaller interactions as possible, but still had a good few days, 10 days of good science. And then some fun here. We're playing soccer there. That's at the end of it. And I guess my time is over, and then I have to acknowledge the contribution of my group members: Alexandra Spiridon, Kilug, Alexandra, Dana Tudor, Ionut Stefanescu, Juliana Stanciu, Madalina Ravar, and all other people from the international laboratories. I don't have pictures with the people in the international collaborations, but this is my group. I thank you for your attention.
Thank you very much for your very nice talk. So questions, please. Okay, if there is no any questions, I'd like to express my sincere thanks once more to Professor Trej. And our next speaker is Raja Chamahi. Title his talk is Anisotropy Control in Photoelectron Spectra, Coherent to Pulse and Interference Strategy.
Yaka mikrofonu. Can you speak?
It's okay. It's okay or no?
Ha, çalışıyor da ses biraz az.
It's not okay. It should.
No, it should be.
I think it's okay.
Okay.
I think it's okay. Yes. Can you please make me some picture?
Okay.
Okay. And this in my
this,
hand, you have
yeah.
laser. So this or
you don't need to hold in your hand.
and
the pocket.
I can make it in my hand.
Okay.
No problem. I can start. Hello, everybody. It's okay. I am Raja Chamahi, a doctor of physics from University of Tunis Al-Manar, Faculty of Science of Tunis. My speech will be about anisotropy control in photoelectron spectra and I will speak about a coherent two-pulse interference strategy. This work, it's a part of collaboration between our group directed by Professor Mourad Telmini from Faculty of Sciences of Tunis, and the group of from University the group of Eric Charon and Osman Atabek from University Paris Sud in France. So the idea of is, can you please? Pointer? The pointer, it's okay, but I can't switch. I can't switch the next slide. Where? Here. It's okay. Okay. So, sorry. So the idea of this work is to study the photoionization of the molecule, the atomic molecule, especially lithium dimer molecule, to have an idea of the angular distribution of the photoelectron spectra using two ultra short laser pulse duration. So before speaking about the phenomena, I will recall first the molecular structure of the lithium dimer molecule. So I present here, as you can see, the potential energy for the for the ground station of the molecular dimer energy, which is labeled by the X state. And the first excited state energy for the A state, and the second excited for the lithium dimer molecule. And finally, we show here the ground state of the lithium ionized molecule labeled by X state. And also their revibrational number, quantum number associated, like you see here, V plus and N plus. So for more detail, I make a zoom for the E state, like you see here, and we present with a line, green solid line, like you see here, the vibrational level, and with the red solid line, the rotational level. So in our work, we will interested of the first vibrational level, which is VE equal 0. So to study the theoretical work of the photoionization of lithium, lithium-2, which is based on the three-step photoionization. So like you see here, 3-step. So we will start with the preparation, the first step, and after that, the pump laser, and finally the probe laser. So for the first step, like you see here, we can, if we launch, we use OCW, a continuous wave, to launch about the first state here for Vx equals 0 and Nx equals 0 to prepare a first state, a first state of the A state electronic potential. And and like you see here, using OCW laser is characterized by a long time duration, which according to the Heisenberg uncertainty principle, we can have only a small bandwidth spectral, like you see here. So only we can excite only the well-determined state. The second step is start with this row vibrational state, and it prepare one of the two possible rotational number, NE equals 0 or NE equal 2. And here we use also the OCW laser. And finally, the third step is concern the to ionize the molecule, and it's prepare a superposition of ion rotational level, like you see here, n plus equals 0 and n plus equal 2. If we start off the NE equals 0, and it also we can reach 3 superposition rotational ion rotational level when we start off NE equal 2. And here we use a femtosecond laser. So we can so with this laser we can excite a superposition of different ion rotational level. So here we consider also that a Franck-Condon principle, it's have a favorite overlap, like you see here, for the first vibration the first vibronic state, VE equals 0 and V plus equals 0. And for this, we see like in this diagram that we have a Franck-Condon factor, which is near to 1, and we have here a good superposition of the two wave packet, like you see here, for the key V plus wave function and VE wave function. And after that, we have two suppositions here, two cases to speak. The first case is we do a photonization of the molecule using a single ultra short pulse with a classical expression of the field laser. So this work is it's published in the GChemPhys 2017 year. For more detail, you can see this publication. And we can also use speak about photonization of the molecule using two ultra short pulse delayed in time, using this probe field, which depends of the time dilated, like you see here with tau. So this work is published in the Physical Review A 2019, and today I will speak about this work. So, like you see here, the spectra show the two probe field of the pump 1 and the probe 1 with a delay time 2. And this is with a particular time duration with 50 femtoseconds for pump and the probe, which are equal. And we will see the variation of the delay tau, what happened in the asymmetry parameter. So the outline of my speech will be as follows. I will start with motivation, and the second part is I will recall briefly a theoretical model. The third part and the fourth part will be, I will present some result of the case of the first rotational level NE equals 0 and the second or the excited rotational level NE equal 2, like you see. And I will finish with a conclusion and some perspective. So, the idea here, like I said, will interest to the two state, the A state of the lithium dimer molecule and the ground state of the X lithium dimer molecule ionized. So, like you see here, if we start with the Rovibronic level, VE equals 0 and NE equals 0, we can reach a superposition of two ion rotational level, N plus equals 0 and 2. And if we start with 2, we have a 3 superposition ion rotational. And for more detail, as I said previously, the delay time will be typical in the femtosecond to picosecond range, and we will interest to the electric field using this expression. With FT, here we consider E0 is the amplitude of the laser, omega is the frequency of radiation, and the FDT is the envelope pulse, E is the polarized laser. So we have here two excitation process. The first one, when we start of NE equals 0, we can reach N plus equals 0 and N plus equal 2. And the second case, we start with NE equal 2, and we can reach N plus equals 0, 2, or 4. So now I speak about a theoretical model. The time-dependent Schrödinger equation is written as low, and we can solve this expression using many using a split operator method. And if you can see the total wave packet psi total can be written as a sum of the psi of the E state, the function of the E state, and the ionized state. And in the Boron-Oppenheimer approximation, this wave function can be a product of the time-dependent wave packet, nuclear wave packet, and independent time of the electronic wave function for the two, for the state E and the the ionized state. And using some important equation and projecting about in the rotational and electronic state, we can have a closed couple of the equation for the E state and for the ionized state using nuclear Hamiltonian, which is the total, like C, where alpha can be considered as the E state for Le or the X state for Le plus. And to solve this equation, we will propagate the nuclear wave packet for the E-state and for the ionized state using a split operator method based to propagate with the Hamiltonian, or total Hamiltonian, which continue the kinetic energy, the potential energy, and the interaction, which is split in 3 parts. And we can write like this in the third order of the split operator. So the question here is how to get a numerical result. Like we know that the kinetic energy, the kinetic propagator and the potential propagator is based in the position space and in momentum space and position space respectively. So we can, using fast Fourier transform, we can go to one representation to the other using, like you see here, to get a final wave function solution. So we move now to the equation, to the expression of the photoelectron angular distribution. Like you see here, it's the sum of the probability which depend of the energy and the angular of this ejected photoelectron, where the probability can be written as flow. So here we can project in the angular ejection, and we found only the spectrum of the photoelectron. And like you see here, using the electric field, this probability also depends of the time delay, and it's depend of the cosine function. So we will see in the result some interference, interference control for specific time in the angular distribution and in the asymmetry parameter for ejected wave function, ejected photoelectron. So here, like I said, for several specific time delay, we can speak about constructive or destructive interference. For example, if we take even number of as a function of duration here, we will speak about constructive interference. And if we take an odd number of dilated time here, tau, as a function of the same time, we can speak about destructive interference. Now I will speak about photoelectron angular distribution, which is where the beta, the asymmetry parameter, defined from the angular differential photonization cross section, where sigma is the total cross section, and P2 is the Legendre polynomial, and beta is the asymmetry parameter. And now if you use our work published in 2017, we can write the photoelectron angular distribution as flow, and we can deduce the asymmetry parameter, which depend of the energy as flow. Now, the asymmetry parameter take value from -1 to 2, and it gives a global idea about the shape of the angular distribution, like you see here. For beta equal -1, you see here that we have an isotropic distribution perpendicular to the laser polarized field. For beta equal 0, we have here isotropic distribution, and also for beta equal 0.5. And final, for beta equal 2, we have here an isotropic distribution along the polarization field. So I will speak now about some result for the NE equals 0. So starting with NE equals 0, we can reach n plus equals 0 and n plus equal 2, like you see here. And if we take here the probability, the spectrum of the energy as a function of the time duration and as a function of the energy, we will see here if we increase the time duration, we have a separate, well-separate peak for n plus equal 2 and n plus equal 0. But when the time duration is less than 5 picoseconds, we will see only only one peak. So that is mean that for long time duration, we have well separates, but here we have an overlap that makes the n plus equal 0 and n plus equal 2. So in our work, we will interest about an ultra short pulse, which is here. So like you see here for the 3G, the 3G plot, when we take tau, the time dilated equal to 0, we see here that the spectrum of photoelectron depend of theta, and it has maximum for theta equals 0 and theta equal p, and it is symmetrical with the theta equal 90 degree. So now, if this is the result of a single pulse, when we take time delay equals 0, and now when we increase the delay time, we see here an oscillatory behavior, like you see here, for t equal 150 femtoseconds. And that is mean that we have an interference, an important interference strategy that we will speak that I will speak in the following slide. So, and now if we take a collection of the delay time, like you see here, to 0 from 0 to 250. You see here that the behavior of the spectrum, the probability of the ejected photoelectron increase with the time delay, and we have a good behavior with an oscillatory spectrum, like you see here. Now I will speak about the angular distribution. So if we study the beta asymmetric parameter when we increase the time duration, we'll see there are two well separate curve for n plus equals 0 and n plus equal 2. And in our work, we will, and in the recent work, I will interest only for the time duration for the low time duration. So short time duration. So for t equal 50 femtoseconds, we see here the behavior of the asymmetric parameter when we increase the time duration, like you see here, and we see an oscillatory behavior for n plus equal 0. And we plot here for specific value of the time delay upload of distribution, this angular distribution. And for n plus equal 2, like you see here, we have also an oscillatory pattern. And as you can see here, we have the plot of the angular distribution, which is isotropic case for TA and TC here, but in tau B, it's isotropic. It's an isotropic case. So, like we see here, for typical specific time duration, for example, if we concentrate of TA, tau A and tau C, we see here that there are a good separation between the behavior curve of n plus equals 0 and n plus equal 2. And if we calculate using a model, a theoretical model, we will see here that tau A it's written by by an odd number multiplied by 5.45 picosecond. And here tau C it's also equal to 3, which is odd number multiplied by 5.45 picosecond. And it is clear here that we have destructive interference, like you see. But here, like you see, it's multiplied by an even number which is equal to 2 multiplied by this value of the time delay. And we will speak here about constructive interference. So now I will speak about the last result, which is concerned to the NE state, NE equal 2. So from NE equal 2, we can reach a superposition of ion rotational level, n plus equals 0, 2, and 4. And as you like here, we have we plot the asymmetry parameter as a function of 2 at the specific energy for n plus equals 0, n plus equal 2, and n plus equal 4. And as you like here, as you can see here, we plot also a polar distribution for some specific value. And the behavior of the angular distribution move to isotropic distribution to anisotropic distribution. So for this, for some value, you can see here, for example, a specific destructive interference. Here also, here, because the orange dashed line is not clear here. Well, destructive interference here also. And it's confirmed our prediction for the theoretical model. And finally, I will speak about angular distribution for the n plus equal 0, n plus equal 2, and n plus equal 4. And we have here a plot of distribution, angular distribution as a vertical, which plot every 1 picosecond, like you see here. And expect the n plus equal 2 when we have the similar angular distribution, isotropic, anisotropic angular distribution. We see here a red field surface for some particular time delay, like you see here, which correspond to the time delay spoken previously. So I will finish with some conclusion. We we are study the theoretical study of the ionization of the lithium molecule using a two ultra-short pulse separated by a time duration. And we also control the photonization process with for the angular and the angular spectrum. We also see a specific phenomena of constructive or destructive interference behavior for some exit channel. And finally, we extract some and control the asymmetry parameter as a function of the time delay. And as a perspective, we can use this theoretical model to other diatomic molecule. And we can also see to additional ultra-short bursts in the train with different time delay and see what happened of the control of the photonization scheme. And finally, we can switch off to dissociative photonization and see what happened about the control strategy. This result it's published in the Physical Review A 2090. If you you can see more detail here, and I like to thanks thanks the Palm Palm of the University Paris Sud for the grants that make me support financial support from Institute of Science of Molecular, and like also to thank my team, my team, which is Mourad Telmini from Faculty of Science of Tunis, Professor Eric Charan from Institut des Sciences Moléculaires d'Orsay, Université Paris Sud, and Dr. Osman Atabek, also from the same university. And also, I'd like to thank the organizer for this nice Congress, and thank you a lot for your attention.
Okay, thank you very much for your very interesting talk. Any question, please? No questions. I think that it is lunch time, and I wish
okay, thanks.
Any success for you and all next speakers. And we are finishing our session.
It's okay for the photo.
Thank you very much.
One from this. Okay.